Hello there, gentle wanderer of the night. Thank you for choosing to spend these quiet moments with me, drifting through the cosmos from the comfort of wherever you are right now. Tonight, we're embarking on a gentle journey through space's most wonderfully weird secrets. We'll discover diamond rain on distant worlds, meet storms older than nations, and visit places where the very laws of physics seem to whisper impossible things. Before we begin our cosmic wandering, I'm curious, where in the world are you listening from right now? And what time is it where you are? I love imagining all the different corners of Earth where these space stories might be floating. If you find yourself enjoying this peaceful exploration of the universe's oddities, a gentle like or subscription would mean the world to me. It helps me know that these quiet cosmic journeys bring you the same wonder they bring me. I should probably warn you, side effects of this journey may include a sudden urge to stare at stars for uncomfortably long periods. It's an inexplicable need to tell people about hexagonal storms, and the persistent feeling that you're made of ancient stardust, which technically you are. So settle in, let your breathing slow, and allow your mind to float freely among the stars. Tonight, the universe has some beautifully strange stories to tell, and we have all the time in the cosmos to listen. Picture, if you will, a storm that forgot it was supposed to be chaotic. At Saturn's North Pole, nature has drawn something that looks like it belongs in a geometry textbook rather than swirling through space. A perfect hexagon, each side stretching across distances that could swallow Earth whole. This isn't just any storm, it's a hexagonal hurricane with sides so precise, so mathematically perfect, that when scientists first spotted it through Voyager's cameras in the 1980s, they wondered if their instruments were playing tricks on them. How could something in nature be so geometric? Geometric. Imagine standing at the center of this hexagon, though of course you'd need to be floating in a very sturdy spacecraft, breathing bottled air, because Saturn's atmosphere isn't particularly welcoming to creatures like us. From that vantage point, you'd see walls of swirling clouds rising around you, each edge of the hexagon perfectly straight, meeting its neighbors at exactly 120-degree angles. It's as if some cosmic engineer decided to practice drawing shapes in the sky. The hexagon spans about 20,000 miles across, wider than two Earths placed side by side. Wind speeds clock in at around 200 miles per hour, which sounds terrifying until you remember that some hurricanes on Earth can reach similar speeds. But Earth's hurricanes are beautifully chaotic, swirling in organic spirals. Saturn's storm insists on sharp corners and straight lines. What makes this geometric marvel even more fascinating is its longevity. This isn't a storm that formed yesterday and will dissipate tomorrow. Scientists believe it's been maintaining its shape for decades, possibly centuries. While weather on Earth changes with seasons, Saturn's hexagon rotates steadily, keeping its form like a patient celestial clock. If you form this geometry as a pro storm it's everywhere. The secret to this cosmic geometry lies in the complex dance of atmospheric flows. Think of it like a river, finding the most efficient path through a landscape. Except this river is made of gas, moving through three-dimensional space, influenced by Saturn's rotation, its magnetic field, and the gravitational pull of its many moons. Sometimes, when all these forces balance just right, nature chooses order over chaos. At the very center of this hexagon sits another marvel, a conventional circular storm, like a normal hurricane that decided to build a geometric fence around itself. This central storm has its own eye, complete with the eerie calm that hurricane eyes possess. So within this mathematical marvel, there's a perfectly ordinary tempest, as if Saturn couldn't decide between being weird and being normal, so it chose both. Scientists have recreated similar hexagonal patterns in laboratory experiments, spinning fluids at different rates and watching geometric shapes emerge from the turbulence. It turns out that under the right conditions, rotating fluids naturally organize themselves into polygons. Nature, it seems, has a hidden fondness for geometry that emerges when the conditions are just right. The hexagon also changes with Saturn's seasons. Yes, Saturn has seasons, though each one lasts about 7 Earth years. During Saturn's northern winter, the hexagon becomes harder to see, shrouded in the planet's seasonal darkness. But as spring arrives and sunlight returns to the northern hemisphere, the hexagon emerges again, as reliable as any earthly seasonal phenomenon. What's perhaps most beautiful about Saturn's hexagon is what it represents, a reminder that the universe is full of patterns we're only beginning to understand. In a cosmos that often seems random and chaotic, here's a storm that insists on perfect geometry, spinning quietly in the outer solar system, like a cosmic mandala drawn in clouds and wind. As you drift towards sleep tonight, imagine that hexagon rotating slowly above Saturn's north pole, its edges maintaining their mathematical precision through the long Saturnian night. Sometimes the universe reveals its hidden order in the most unexpected places, even in the heart of a storm that's been spinning since before your grandparents were born. 40 light-years away from Earth, in the constellation Cancer, there exists a world that would make every jeweler in history weep with envy. Meet 55 Cancri E, a planet where the ground beneath your feet wouldn't be soil or rock, but crystallized carbon, pure diamond, stretching from horizon to horizon. This isn't just a planet with some diamond deposits scattered about like Earth's precious gems hidden deep in mines. No, this entire world is essentially one massive diamond, roughly twice the size of Earth, orbiting so close to its star that its year lasts only 18 Earth hours. Imagine celebrating your birthday every 3/4 of a day. The story of how a planet becomes made of diamond reads like a cosmic recipe gone wonderfully mad. You start with a star that's incredibly rich in carbon, much more so than our sun. Over billions of years, this carbon-heavy stellar wind gets captured by a forming planet. Add tremendous pressure from the planet's own gravity, mix in temperatures that would melt copper and wait a few billion years. The result, a world where the very bedrock sparkles. But here's where things get even stranger. The surface temperature of 55 Cancri reaches about 3,900 degrees Fahrenheit, hot enough to melt gold, silver, and most other metals we consider precious. So while you might be standing on the most valuable ground in the known universe, you'd also be experiencing heat that would turn you into plasma faster than you could say engagement ring. The planet is tidally locked to its star, meaning one side always faces the blazing heat, while the other side experiences eternal night. The day side glows like an ember, while the night side might be cool enough for the diamond surface to remain solid. If you could somehow survive a visit, you'd witness the most dramatic temperature gradient imaginable, from molten diamond seas to solid crystal plains, all on the same world. Scientists estimate that about 1/3 of 55 Cancri-E's mass consists of diamond. To put that in perspective, if you could somehow harvest just a tiny fraction of this planet's surface, you'd have enough diamonds to crash every gem market on Earth for the next 1,000 years. The entire planet is worth more money than has ever existed in human history. Not that currency would mean much on a world where the atmosphere is probably vaporized rock. What's particularly enchanting about this diamond world is how it challenges our Earth-centric ideas about planetary formation. We're used to thinking of planets as being made of the familiar materials we know, iron cores, rocky mantles, perhaps some ice. But the universe is far more creative than that. When conditions are just right, entire worlds can crystallize into forms that seem more like fantasy than science. The discovery of 55 Cancri also hints at the incredible diversity of worlds that must exist throughout the galaxy. If one star system can produce a diamond planet, what other impossible worlds are spinning through space? Perhaps there are planets made of other precious materials, or worlds with physics so strange they'd rewrite our textbooks. Observing this glittering world isn't easy. It's far too distant to see directly, even with our most powerful telescopes. Instead, astronomers detect it by watching for the tiny dimming that occurs when the planet passes in front of its star. From that brief shadow, they can deduce the planet's size, orbit, and composition. It's like determining that someone is holding a diamond by watching how it affects a distant streetlight. The diamond planet also makes us reconsider what we mean by precious. On Earth, diamonds are valuable partly because they're rare, but in a universe containing entire worlds made of diamond, rarity becomes relative. Perhaps what's truly precious isn't the material itself, but the rarity of worlds that can support the complex chemistry we call life. As you settle into sleep tonight, let your mind wander to that distant, sparkling world. Picture the way starlight might refract through its crystalline surface, creating rainbows that dance across landscapes no human eye will ever see. In the grand cosmic jewelry box of the universe, hummingbirds spinning quietly, a reminder that even the most precious things we can imagine are just everyday building materials for planets in other star systems. Sometimes the universe's extravagance is almost absurd. An entire world made of what we consider the most precious of stones, blazing away in the darkness, beautiful and completely indifferent to our earthly notions of value. In the cosmic graveyard where massive stars go to die, something extraordinary happens. The star doesn't simply fade away like a candle burning out. Instead, it creates one of the most mind-bending objects in the universe, a neutron star, where physics pushes matter to its absolute breaking point. Imagine trying to compress all of Mount Everest into a space the size of a sugar cube. That's essentially what happens when a neutron star forms. Except instead of a mountain, it's the entire core of a star that once blazed with the fury of 1,000 suns. The result is matter so dense that a single teaspoon of it would weigh about 6 billion tons, roughly the same as all the automobiles on Earth combined, squeezed into something you could stir into your coffee. But let's slow down and savor just how impossible this seems. Picture holding a teaspoon, that familiar kitchen utensil you might use for honey or sugar. Now imagine that this innocent little spoon contains matter so dense that if you somehow brought it to Earth, it would punch through the planet like a bullet through tissue paper. Its gravity so intense that it would begin consuming everything around it. The birth of a neutron star is one of nature's most violent spectacles. When a massive star, at least 8 times heavier than our Sun, runs out of nuclear fuel, it faces a cosmic crisis. For millions of years, the star has maintained a perfect balance, nuclear fusion pushing outward, gravity pulling inward. But when the fuel runs out, gravity wins catastrophically. In less than a second, the star's core collapses. Imagine a sphere larger than Earth suddenly compressing to the size of Manhattan. The collapse happens so fast that the outer layers of the star don't even have time to notice what's happening before they slam into the ultra-dense core and rebound in a supernova explosion, visible from billions of miles away. What remains is something that stretches our understanding of matter itself. In the crushing embrace of neutron star gravity, about 200 billion times stronger than Earth's individual atoms, simply cease to exist. Protons and electrons are squeezed together so tightly they merge into neutrons, creating a sea of nuclear matter unlike anything that naturally exists anywhere else in the universe. The surface of a neutron star is a landscape that defies imagination. It's probably crystalline, harder than diamond, yet so smooth that any surface irregularities would be measured in millimeters. The gravity is so intense that if you could somehow stand on this surface, which you couldn't because you'd be flattened into a layer of atoms, a single step would require more energy than climbing Mount Everest on Earth. These stellar corpses spin with precision that puts the finest Swiss watches to shame. Some neutron stars rotate hundreds of times per second, their surfaces moving at significant fractions of the speed of light. As they spin, they emit beams of radiation like cosmic lighthouses, sweeping across space with clockwork regularity. We call these pulsars, and they're so precise that astronomers use them as natural atomic clocks, timing their pulses to study the fabric of space-time itself. The magnetic fields around neutron stars are equally extreme, trillions of times stronger than Earth's magnetic field. These fields are so powerful, they could erase the magnetic strip on your credit card from thousands of miles away. If a neutron star with a typical magnetic field were placed halfway between Earth and the Moon, it would wipe clean every hard drive, credit card, and magnetic storage device on our planet. Perhaps most remarkably, neutron stars help us understand one of physics' deepest mysteries: what happens to matter under the most extreme conditions possible. The cores of these stars exist in a state that we can barely begin to understand, where the normal rules of matter and energy are pushed beyond their limits. Some scientists theorize that the very centers of neutron stars might contain exotic forms of matter that don't exist anywhere else. Strange quarks arranged in configurations that sound more like science fiction than science fact. Yet, for all their cosmic violence and impossible physics, neutron stars also represent something beautiful. They're the ultimate recycling centers of the universe. The heavy elements that make up your body, the calcium in your bones, the iron in your blood, were forged in the cores of massive stars and scattered into space when those stars died and became neutron stars or black holes. As you drift towards sleep, consider this: somewhere in the darkness between the stars, these impossible objects spin silently, each one a testament to the universe's ability to create conditions so extreme they challenge everything we think we know about reality. They're cosmic time capsules, preserving in their super-dense hearts the final moments of stellar death, spinning through eternity as monuments to the beautiful violence of stellar evolution. In their own way, neutron stars are the universe's way of showing us that even in death, stars can create something magnificent and strange, objects so dense with mystery that they'll keep scientists wondering for generations to come. If you could somehow step far enough back from the universe, farther than any human mind can truly imagine, you'd witness something wonderfully familiar yet utterly vast. And the largest structures in existence don't look like the solid, imposing architecture you might expect. Instead, they resemble the delicate, translucent walls of soap bubbles floating in a cosmic bath. This is the cosmic web, and it's one of the most beautiful discoveries in modern astronomy. Imagine blowing bubbles in your backyard on a summer evening, watching them drift and cluster, their walls catching the light while vast, empty spaces exist between them. Now picture that same pattern, but instead of soap film, the bubble walls are made of galaxies, billions upon billions of stars organized into shimmering threads that stretch across hundreds of millions of light years. The structure emerged gradually, like a photograph developing in slow motion over billions of years. In the early universe, matter wasn't evenly distributed. There were tiny variations in density, some regions slightly denser than others, some slightly more empty. Gravity, patient and persistent, began pulling matter toward the denser regions while emptying out the less dense areas. The structure emerged gradually, like a photograph developing in slow motion over billions of years. Over cosmic time, this process created something remarkable. Vast filaments of galaxies connected like luminous highways through space, surrounding enormous voids that are almost perfectly empty. These voids are so large that if you lived in a galaxy at the center of one, you might look up at the night sky and see almost nothing, just a few scattered stars from your own galaxy, with the nearest neighboring galaxies so distant they'd be invisible to the naked eye. The biggest surprise is how much of the universe is actually empty space. The cosmic web consists mostly of these vast voids, with galaxies clustered along the thin filaments like cities connected by interstate highways. If the universe were a house, the galaxies would be like the furniture, and the voids would be all the empty rooms in between. Except in this case, the empty rooms make up about 80% of all the space. What's particularly enchanting is how this structure mirrors patterns we see in completely different contexts. The cosmic web looks remarkably similar to the neural networks in your brain, with nodes connected by branching pathways. It resembles the mycelial networks of fungi spreading through forest soil, or even the large-scale structure of cities connected by transportation networks. There's something profound about the way the universe organizes itself into these familiar patterns at every scale. Scientists map this cosmic web using the light from distant galaxies and quasars. When light travels through the universe, it passes through clouds of hydrogen gas that exist along these filaments. The gas absorbs specific wavelengths of light, creating a sort of cosmic barcode that reveals where matter is concentrated and where it's absent. It's like using shadows to map the skeleton of creation itself. The filaments themselves are not solid structures, but rather regions where galaxies congregate, like cars naturally clustering on busy highways. These galactic highways are fed by streams of dark matter, that mysterious substance that makes up most of the universe's mass, but doesn't emit light. The dark matter provides the gravitational scaffolding upon which ordinary matter can collect and form stars, planets, and eventually curious creatures like us, who wonder about cosmic architecture. One of the most remarkable aspects of the cosmic web is its delicate balance. The filaments are held together by gravity, but they're also being stretched apart by the expansion of space itself. It's a cosmic tug-of-war that's been playing out for over 13 billion years, with the web slowly evolving as the universe ages and expands. In the distant future, as space continues expanding and galaxies drift farther apart, this beautiful web structure will gradually fade. The filaments will stretch and thin until individual galaxies become isolated islands in an increasingly empty cosmos. But for now, in this particular moment in cosmic history, we exist during the era when the universe displays its most magnificent, large-scale architecture. What makes this even more personal is realizing that we're part of this structure. The Milky Way galaxy sits on one of these cosmic filaments, connected to the vast network that spans the observable universe. When you look up at the night sky, you're seeing your local neighborhood in this cosmic web, the nearby galaxies that share our particular filament of the universe's largest architecture. The cosmic web also reminds us that structure and emptiness are both essential to the universe's beauty. Without the vast voids, there would be no contrast to appreciate the galaxy-rich filaments. Without the empty spaces, matter might be spread too thinly to form the dense regions where stars and planets can emerge. As you settle into sleep tonight, imagine yourself floating in one of those cosmic bubbles, surrounded by walls made of distant galaxies, their light twinkling like Christmas decorations strung across the darkness. In the cosmic web, we're all residents of the same vast, delicate structure, citizens of bubble walls made of starlight, drifting through the universe's grandest architectural marvel. It's oddly comforting to know that even at the largest scales imaginable, the universe chooses patterns that feel familiar, creating cosmic soap bubbles that would look perfectly at home floating through your backyard on a quiet summer evening. There's something wonderfully rebellious about Venus, our nearest planetary neighbor. While every other planet in our solar system spins in the same direction, the direction established when the solar system first began forming from a spinning disk of gas and dust, Venus decided to be different. It spins backwards, like a cosmic contrarian refusing to follow the crowd. But Venus's relationship with time gets even stranger than simple backwards rotation. If you could somehow survive on Venus's surface, which you couldn't, because it's hot enough to melt lead, and the atmospheric pressure would crush you like an empty soda can, you'd experience one of the most peculiar calendar systems imaginable. A day on Venus, measured from one sunrise to the next, lasts 243 Earth days. But a Venusian year, the time it takes to orbit the sun, is only 225 Earth days. Think about that for a moment. The planet spins so slowly that its day is longer than its year. If you lived on Venus, you'd celebrate your birthday before you'd experience a complete day-night cycle. You could have multiple anniversaries, finish entire projects, maybe even learn a new language, all while waiting for the sun to complete its journey across the Venusian sky. The backwards rotation means that on Venus, the sun rises in the west and sets in the east, assuming you could actually see the sun through Venus's thick, opaque atmosphere of sulfuric acid clouds. It's like living in a world where all the basic assumptions about daily life have been turned upside down. East becomes west, west becomes east, and time itself seems to flow in unexpected directions. Scientists think Venus's backward spin resulted from a catastrophic collision early in the planet's history. Imagine a cosmic billiard ball game where a massive object, perhaps another planet or a very large asteroid, slammed into Venus with such force that it literally knocked the planet over, causing it to tumble and eventually settle into its current backwards rotation. It's as if the universe played a practical joke on Venus, leaving it permanently dizzy and spinning the wrong way. This collision theory helps explain why Venus is so different from Earth, despite being roughly the same size and mass. Venus is often called Earth's twin, but it's more like Earth's evil twin, who decided to embrace extremes. Where Earth has comfortable temperatures and breathable air, Venus chose crushing atmospheric pressure and surface temperatures of 900 degrees Fahrenheit. Where Earth rotates sensibly, Venus spins backwards. Where Earth has reasonable day-night cycles, Venus decided that days should last for months. The slow rotation has profound effects on Venus's weather and geology. Without the moderating influence of regular day-night cycles, heat doesn't get distributed evenly around the planet. Instead, Venus maintains an almost uniform temperature across its entire surface, equally scorching whether you're on the day side or night side, at the poles or the equator. It's like a planetary oven set to incinerate with no timer to turn it off. Venus's sluggish spin also affects its magnetic field, or rather the lack thereof. Earth's magnetic field is generated partly by our planet's relatively rapid rotation, which helps stir the molten iron in our planet's core. Venus bends so slowly that it can't generate a significant magnetic field, leaving it vulnerable to the solar wind, stripping away its atmosphere over geological timescales. The backwards rotation creates some interesting observational effects for astronomers. When Venus passes between Earth and the Sun, an event called a transit, the planet appears to move across the Sun's face from east to west, opposite to how other planets transit. It's a small detail, but it serves as a visible reminder of Venus's contrarian nature. What's perhaps most poetic about Venus's backwards dance is how it challenges our assumptions about planetary behavior. We tend to think of the solar system as orderly and predictable, with planets following neat rules and patterns. But Venus reminds us that cosmic history is full of chaos, collisions, and accidents that can fundamentally alter a world's character. Venus also makes us appreciate Earth's more conventional relationship with time. All 24-hour days and 365-day years feel natural to us, but they're the result of specific circumstances in our planet's formation and evolution. The regular rhythm of day and night, the seasonal changes that mark the passage of years. These are gifts that not every world receives. If you were somehow immortal and could visit Venus, you'd need to completely reimagine how you think about time. Forget about daily schedules, morning routines, or evening plans. On Venus, you'd measure time by years rather than days, watching the stars wheel slowly overhead as the sun took nearly 8 Earth months to cross the sky. As you drift towards sleep in Earth's comfortable 24-hour rhythm, take a moment to appreciate the gentle regularity of our planet's dance with time. Tomorrow the sun will rise in the east, just as it has for billions of years, marking another day in Earth's steady rotation. Meanwhile, Venus continues its slow, backwards waltz around the sun, a reminder that in the cosmic dance of planets, not everyone follows the same steps. Sometimes the most beautiful thing about our cosmic neighborhood is its diversity. Worlds that chose different paths, different relationships with time, and different ways of spinning through the darkness between the stars. Deep in the heart of our galaxy, about 26,000 light-years from Earth, there exists what might be the universe's most impressive brewery. Sagittarius B2 is a massive cloud of gas and dust that's been quietly distilling alcohol for millions of years, producing quantities of ethyl alcohol that would make every distillery on Earth seem like a hobbyist's basement operation. This isn't just a little alcohol floating around in space. We're talking about a cloud that contains enough ethyl alcohol to fill about 400 trillion pints of beer. To put that in perspective, if every person who ever lived consumed alcohol at the rate of the most enthusiastic college student, we still wouldn't make a dent in Sagittarius B2's cosmic reserves. But the universe's distillery doesn't stop at simple ethyl alcohol. This cosmic cloud also produces methanol, formaldehyde, and other organic compounds that form the basic building blocks of more complex chemistry. It's like a massive natural laboratory where the universe experiments with the molecules that could eventually become the chemistry of life. The alcohol forms through a process that's surprisingly similar to how we make alcohol on Earth, just on an incomprehensibly larger scale. In the cold depths of space, where temperatures hover just a few degrees above absolute zero, carbon-rich molecules bump into each other in slow-motion dances that span thousands of years. when conditions are just right, when there's enough dust to shield the molecules from harsh stellar radiation, and enough time for complex chemistry to unfold, simple carbon compounds gradually transform into more complex organic molecules. Sagittarius B2 is particularly good at this cosmic chemistry because it's located near the center of our galaxy, where there's an abundance of the heavy elements needed for organic molecule formation. For Corius, the region is also rich in dust grains that serve as tiny factories, providing surfaces where molecules can stick together and react in ways that wouldn't be possible in the emptiness of space. What makes this discovery delightfully absurd is that when radio astronomers first detected these alcohol signatures in the 1960s and 70s, they were using radio telescopes to study the structure and composition of interstellar clouds. They weren't looking for cosmic cocktails. They were trying to understand star formation and galactic structure. Instead, they found that space is apparently well stocked with the raw materials for the universe's most extensive happy hour. The alcohol molecules reveal themselves through radio waves. Each type of molecule absorbs and emits radio energy at specific frequencies, creating a kind of cosmic fingerprint that radio telescopes can detect. When astronomers point their instruments at Sagittarius B2, they receive radio signals that translate directly to "there's a lot of alcohol here." It's like the universe is broadcasting its own chemical analysis. This cosmic distillery also tells us something profound about the potential for life in the universe. The same processes that create alcohol in space also create many other organic compounds that are essential for biology. Amino acids, sugars, and other complex molecules have all been detected in interstellar clouds, suggesting that the building blocks of life are being manufactured throughout the galaxy. The scale of Sagittarius B2 is almost impossible to grasp. The cloud is about 150 light-years across. If you could travel at the speed of light, it would take you 150 years to cross from one side to the other. The total mass is several million times that of our Sun, making it one of the most massive molecular clouds in our galaxy. And within this vast region, countless chemical reactions are slowly converting simple molecules into more complex forms. What's particularly wonderful about this cosmic chemistry set is its patience. Unlike industrial processes on Earth that happen in minutes or hours, the alcohol production in Sagittarius B2 unfolds over millions of years. Molecules drift through space at leisurely speeds, occasionally bumping into dust grains or other molecules, gradually building up complexity through countless small interactions. The discovery of alcohol in space also sparked some wonderfully irreverent calculations by astronomers with a sense of humor. If you could somehow harvest all the alcohol in Sagittarius B2 and transport it to Earth, every person on the planet could have several trillion bottles of pure ethanol. Of course, ethanol isn't exactly a pleasant beverage by itself, and the logistics of interstellar alcohol transportation presents certain challenges. But beyond the amusing implications, Sagittarius B2 represents something beautiful about the universe's chemistry. The same physical processes that created the alcohol in this distant cloud also contributed to the formation of the organic molecules that eventually became part of the chemistry of life on Earth. We're all connected to this cosmic distillery through the long chain of chemical evolution that spans from interstellar space to living cells. As you settle into sleep tonight, imagine that vast cloud of alcohol floating silently in the center of our galaxy, slowly brewing its cosmic cocktails in the patient darkness between the stars. It's a reminder that the universe is constantly creating complexity from simplicity, building the molecular foundations for chemistry, biology, and eventually, creatures curious enough to discover cosmic distilleries hidden in radio waves. In its own way, Sagittarius B2 is the universe's way of showing us that even the most unexpected discoveries await us in space, including enough alcohol to keep the entire galaxy in good spirits for the foreseeable cosmic future. On July 20th, 1969, when Neil Armstrong stepped onto the lunar surface and spoke those famous words about one small step, he left behind something more permanent than his words. Actual footprints that will outlast human civilization, outlast the rise and fall of continents on Earth, and possibly outlast our species itself. Those boot prints pressed into the fine lunar dust aren't going anywhere. There's no wind on the moon to blow them away, no rain to wash them clean, no geological processes to gradually erase them. In the airless silence of our celestial neighbor, Neil Armstrong's first steps on another world remain as crisp and clear as they were the moment he lifted his boot from the regolith. This permanence comes from the moon's lack of atmosphere. On Earth, our footprints in sand disappear. With the next tide, our tracks in mud fade with the next rainfall, and even our footprints in concrete eventually succumb to weathering and erosion. But the moon exists in a state of suspended animation, where the only changes happen on timescales so vast, they make human history seem like a brief moment. The lunar regolith, that fine powdery dust that covers the moon's surface, is the result of billions of years of meteorite impacts. With no atmosphere to burn up incoming space rocks, even tiny meteoroids slam into the moon's surface at tremendous speeds, gradually pulverizing the bedrock into an increasingly fine powder. This powder is so fine that it acts almost like flour, preserving every detail of whatever presses into it. Think about the poetic justice of this preservation. The moon, which has no ability to create or sustain life as we know it, has become the universe's most reliable archivist of human achievement. Every footprint from the 6 Apollo missions that successfully landed astronauts on the lunar surface remains exactly where it was left. 12 pairs of human feet that explored another world. Their impressions now permanently embedded in cosmic history. But it's not just footprints that remain. The moon has become an inadvertent museum of human space exploration. The lunar modules that served as bases for the Apollo astronauts are still there, their gold foil insulation and spindly legs exactly as they appeared when the astronauts departed. Tools left behind by the crews, hammers, sample containers, cameras that ran out of film, all remain precisely where they were abandoned, waiting in the lunar day and night, like artifacts from a civilization that briefly visited and then returned to their blue world hanging in the black sky. The American flags, planted by each Apollo crew, present an interesting case study in lunar preservation. While the fabric flags themselves have likely been bleached white by decades of unfiltered solar radiation, the flagpoles and the impressions made by the astronauts' boots while planting them remain unchanged. It's a reminder that some aspects of human presence fade while others endure, creating an incomplete but permanent record of our brief visits. What makes these lunar preservations even more remarkable is their contrast with how quickly human traces disappear on Earth. Cities rise and fall, forests reclaim farmland, and even our most impressive monuments gradually succumb to time and weather. But on the moon, a casual decision to set down a tool or take an extra step has created permanent marks that will outlast most of what we consider enduring on Earth. The moon's preservation isn't perfect, though. Very slowly, over timescales of millions of years, the footprints will fade as cosmic rays and micrometeorites gradually alter the lunar surface. But this erosion happens so slowly that the footprints could remain recognizable for millions of human lifetimes. Our species could evolve into something completely different, and Neil Armstrong's boot prints would still be there, waiting. There's something both humbling and inspiring about this permanence. The moon, in its cold and airless way, offers a kind of immortality to human achievement that we can't find anywhere else. It's as if the universe provided us with one place where our marks on cosmic history could be preserved indefinitely, a celestial safety deposit box for the evidence of our greatest adventure. Future lunar visitors will be able to see these historical sites, the first human footprints on another world, preserved in perfect detail. It will be like visiting ancient archaeological sites, except these artifacts will be from humanity's first tentative steps into the cosmos rather than our early steps towards civilization. The preservation of lunar footprints also raises interesting questions about space archaeology. As humans return to the moon and eventually establish permanent settlements, how do we protect these historical sites? The first human footprints on another world deserve the same reverence we give to other pivotal moments in human history. As you prepare for sleep tonight, consider those lonely bootprints waiting in the lunar dust, maintaining their vigil through the too weak, lunar day, when surface temperatures reach 250 degrees Fahrenheit, and through the equally long lunar night, when temperatures plummet to minus 250 degrees. Through all of this cosmic extremes, the footprints remain patient, permanent, and perfectly preserved. In a universe where everything eventually changes, where stars are born and die, where planets evolve and species come and go, there's something wonderfully stubborn about those human footprints, refusing to fade, marking forever the moment when life from Earth first walked on another world. Beneath the icy shell of Jupiter's moon Europa lies one of the most tantalizing secrets in our solar system, an ocean that contains more than twice as much water as all of Earth's oceans combined. This isn't just a modest underground lake or a damp subsurface layer. We're talking about a global ocean that could be 60 to 150 miles deep, hidden beneath a frozen crust that may be only 15 to 25 miles thick. To put Europa's oceanic abundance in perspective, imagine taking every drop of water from every ocean, lake, river, and raindrop on Earth, then doubling it. That's what exists beneath the seemingly barren, frozen surface of a moon that's smaller than our own moon. It's as if nature decided to hide the solar system's greatest reservoir of liquid water in the last place you'd expect to find it, on a frozen world orbiting Jupiter in the cold outer reaches of our cosmic neighborhood. Europa's ocean exists because of a cosmic dance of gravitational forces that sounds like something from a physics textbook, but results in one of the most beautiful heating systems in the solar system. As Europa orbits Jupiter, the massive planet's gravity stretches and squeezes the moon like a cosmic stress ball. Sometimes Europa is closer to Jupiter and feels stronger gravitational pull. Sometimes it's farther away and feels less. This constant flexing generates heat through friction, the same way repeatedly bending a paperclip makes it warm. This tidal heating is so effective that it keeps Europa's vast ocean liquid, despite receiving only 1/25th the sunlight the Earth receives. It's like having a planetary heating system that runs on orbital mechanics rather than fossil fuels, completely renewable energy that's been operating reliably for billions of years. The surface of Europa tells the story of this hidden ocean through a network of ridges, cracks, and chaotic terrain that looks like broken sea ice floating on a dark Arctic ocean. These features are likely created when the ocean below pushes up against the ice shell, cracking it, shifting it, and sometimes even allowing water to temporarily reach the surface before freezing in the cold vacuum of space. Scientists have detected water vapor plumes erupting from Europa's surface, geysers of ocean water shooting hundreds of miles into space through cracks in the ice. These plumes offer the tantalizing possibility of sampling Europa's ocean chemistry without having to drill through miles of ice. Scientists have detected water vapor plumes erupting from Europa. It's like the moon is occasionally offering us a taste of its hidden seas, sending samples directly to spacecraft that happen to be passing by. What makes Europa's ocean particularly exciting from a biological perspective is that it's likely in contact with the moon's rocky mantle. This means that the ocean chemistry could be enriched by minerals and possibly even hydrothermal vents, similar to those found in Earth's deep ocean trenches. On Earth, these deep-sea thermal vents support entire ecosystems that thrive without sunlight, living off the chemical energy that emerges from the interaction between water and rock. The possibility of hydrothermal vents on Europa's ocean floor creates a scenario that astrobiologists find irresistible: a warm, mineral-rich environment protected from the harsh radiation of space by miles of ice, with a stable liquid water environment that's existed for billions of years. If life can emerge and thrive in Earth's most extreme environments, perhaps it could also find a way to flourish in Europa's alien seas. Europa's ocean is also incredibly stable. While Earth's surface has been repeatedly transformed by asteroid impacts, volcanic activity, and changing climates, Europa's subsurface ocean has likely remained liquid and relatively unchanged for most of the solar system's history. Any life that might have emerged there would have had billions of years to evolve and adapt, potentially creating ecosystems unlike anything on Earth. The depth of Europa's ocean means it contains vastly more habitable volume than Earth's oceans. While Earth's oceans average about 2.3 miles deep, Europa's ocean could be 60 miles deep or more. That's an enormous three-dimensional space where life could potentially exist at many different levels, possibly developing complex ecosystems with their own versions of deep-sea creatures, mid-ocean species, and organisms that live near the ice ceiling. Exploring Europa's ocean represents one of the most ambitious challenges in space exploration. Any mission would need to either drill through miles of ice or find ways to sample the water plumes that occasionally erupt from the surface. But the potential rewards are extraordinary. Discovering life in Europa's ocean would fundamentally change our understanding of biology and our place in the universe. As you drift towards sleep tonight, imagine that vast, dark ocean hidden beneath Europa's icy shell. Picture the gentle currents flowing through alien waters that have never known sunlight, carrying minerals and heat from the rocky depths to the ice ceiling above. In the profound darkness of Europa's seas, warmed by the gravitational embrace of Jupiter and protected by miles of frozen water, one of the universe's most intriguing mysteries waits patiently to be discovered. Europa reminds us that the most precious things in the universe are often hidden, that abundance can exist in the most unlikely places, and that the cosmos has a talent for preserving possibilities in the most unexpected cosmic neighborhoods. Mercury, the smallest planet in our solar system, and the one closest to the Sun, experiences some of the most dramatic temperature changes imaginable in a single day, which lasts 88 Earth days, due to Mercury's leisurely rotation. This little world swings between temperatures that could melt zinc and temperatures cold enough to freeze carbon dioxide. We're talking about temperature differences of more than 800 degrees Fahrenheit, all happening on the same small planet. During Mercury's long day, when the sun blazes overhead in the airless sky, surface temperatures soar to about 800 degrees Fahrenheit. That's hot enough to melt lead, tin, and zinc, metals that would pool into shiny puddles on Mercury's rocky surface. If you could somehow stand on Mercury during its day, which you absolutely couldn't, for many reasons involving instant vaporization, the ground beneath your feet would be hot enough to cook a pizza in seconds. But here's where Mercury's story takes a fascinating turn. Despite being the closest planet to the Sun, Mercury's nighttime temperatures plummet to minus 300 degrees Fahrenheit, colder than Pluto, colder than the moons of Jupiter, colder than just about anywhere else in the solar system, except the most distant reaches of space. This seems impossible until you understand Mercury's unique situation. The secret to Mercury's extreme temperature swings lies in its complete lack of atmosphere. Earth's atmosphere acts like a thermal blanket, absorbing heat during the day and releasing it slowly at night, which keeps our temperature variations relatively moderate. Mercury has no such blanket. Any heat that builds up during the day radiates directly back into space the moment the sun sets. Mercury's day-night cycle is also remarkably long due to the planet's peculiar rotation. A single day on Mercury, from one sunrise to the next, lasts about 176 Earth days. That means Mercury experiences nearly 3 Earth months of continuous blazing sunlight, followed by nearly 3 Earth months of frigid darkness. It's like the most extreme seasonal affective disorder imaginable, where winter and summer happen twice per Mercury year. The planet's elliptical orbit adds another layer of complexity to its temperature extremes. Mercury's distance from the Sun varies significantly during its 88-day year. Sometimes it's 29 million miles from the Sun. Sometimes it's 43 million miles away. When Mercury is closest to the Sun, it receives more than twice as much solar energy as when it's farthest away, creating additional temperature variations that stack on top of the day-night differences. These extreme conditions create some surreal landscapes on Mercury's surface. During the day, the rocks themselves might glow with heat, creating shimmering thermal mirages in the vacuum of space. Metals that exist as solids on Earth could flow like lava across Mercury's surface during peak heating. Yet just a few hundred miles away, on Mercury's night side, the same rocks become so cold they could shatter like glass if something struck them. Mercury's polar regions present a particularly bizarre situation. Due to the planet's minimal axial tilt, some craters near the poles never receive direct sunlight. They exist in permanent shadow while being on a planet that experiences some of the hottest temperatures in the solar system. These permanently shadowed regions are so cold that scientists believe they may contain deposits of water ice, preserved for millions of years in crater floors that never see daylight. It's a wonderfully contradictory situation. Water ice existing on the planet closest to the sun, preserved in cold traps, while just miles away the surface bakes at temperatures that would melt most metals. It's like finding an iceberg in the middle of a blast furnace, perfectly preserved by the strange geometry of shadows and sunlight. The temperature extremes on Mercury also create interesting effects on the planet's tenuous atmosphere, or more accurately, its exosphere. Mercury does have an extremely thin atmosphere made up of atoms blasted off its surface by solar wind and meteorite impacts. This wispy atmosphere changes dramatically with temperature, becoming denser during the day as more atoms are knocked free from the hot surface, and thinner at night as atoms freeze back onto the cold ground or escape into space. These extreme temperature swings make Mercury one of the most challenging environments imaginable for any kind of exploration. Spacecraft visiting Mercury need special heat shields to survive the intense solar radiation, but they also need heaters to prevent their instruments from freezing when they pass into Mercury's shadow. It's like designing equipment that needs to function in both a furnace and a deep freezer, often within the same mission. Mercury's temperature extremes also remind us how special Earth's moderate climate really is. Our planet's atmosphere, magnetic field, and just right distance from the sun create conditions where water can exist as liquid, where temperatures stay within a range that allows complex chemistry, and where life can emerge and thrive. Mercury shows us what happens when you remove those protective systems, a world of beautiful but deadly extremes. As you settle into sleep in Earth's comfortable, moderate temperatures, take a moment to appreciate the invisible atmospheric blanket that keeps your bedroom at a pleasant temperature all night long. Meanwhile, Mercury continues its slow dance between furnace and freezer, experiencing temperature swings that would instantly destroy any life we know, yet somehow managing to preserve ancient ice in its polar shadows. A reminder that even the most extreme worlds can hold surprising secrets. 4.5 billion years from now, someone standing on Earth, if Earth still exists, and if there are still beings capable of standing and looking up at the night sky, will witness the most spectacular cosmic event visible from our planet. The Andromeda Galaxy, currently a faint smudge of light in our autumn sky, will fill the heavens like a vast spiral of stars, growing larger each night as it approaches our Milky Way in the universe's most majestic slow-motion collision. This isn't the kind of collision you might imagine, with galaxies smashing into each other like cosmic car crashes. Instead, it's more like a graceful dance between two vast collections of stars, a gravitational ballet that will unfold over billions of years. The Andromeda Galaxy is currently racing toward us at about 250,000 miles per hour, which sounds incredibly fast until you realize that at cosmic distances, this means the collision won't begin for longer than life has existed on Earth. The Andromeda Galaxy is our nearest major galactic neighbor, and it's approaching us for reasons that tell a beautiful story about cosmic destiny. Despite the overall expansion of the universe, which is carrying most galaxies away from each other, Andromeda and the Milky Way are gravitationally bound. We're like two dancers who started on opposite sides of a vast ballroom and have been slowly spiraling toward each other for billions of years, drawn together by the inexorable pull of gravity. What makes this cosmic collision even more remarkable is its inevitability. There's no force in the universe that can prevent it, no cosmic steering wheel that can change course. The two galaxies are locked in a gravitational embrace that began when they first formed, and they've been falling toward each other ever since. It's a reminder that even on the largest scales, the universe follows predictable physical laws. Gravity always wins, given enough time. When the collision begins, the night sky will transform in ways that challenge imagination. Andromeda, which currently appears as a faint oval through binoculars, will gradually grow to span the entire sky. For millions of years, beings on Earth we'll be able to watch new stars forming as gas clouds from the two galaxies collide and compress, triggering waves of star birth that will light up the heavens with brilliant blue-white stars. But here's the wonderfully counterintuitive part. Despite this being called a galactic collision, it's likely that very few individual stars will actually collide with each other. Galaxies are mostly empty space, with vast distances between stars. It's like two swarms of bees flying through each other. The swarms merge and mix, but individual bees rarely bump into each other. Most stars will simply be relocated to new neighborhoods in the merged galaxy. Our Sun will probably survive the galactic merger, though it might be flung to a completely different part of the new combined galaxy. Earth might find itself in what was once Andromeda's spiral arm, looking up at a night sky filled with alien constellations made of stars that formed in a different galaxy billions of years ago. It's like the ultimate cosmic moving day. Same house, completely different neighborhood. The merger will also awaken the supermassive black holes that lurk at the centers of both galaxies. Currently, both black holes are relatively quiet, occasionally snacking on nearby gas and dust. But when the galaxies merge, gravitational forces will funnel enormous amounts of material toward both black holes, causing them to flare to life as brilliant quasars that could outshine all the stars in both galaxies combined. Eventually, the two black holes themselves will spiral toward each other in a cosmic dance that will end with their merger into an even more massive black hole. This final black hole collision will release gravitational waves so powerful they'll ripple across the universe, carrying the news of our galactic merger to distant corners of the cosmos. Astronomers have already chosen a name for the merged galaxy, Andromeda, a combination of Milky Way and Andromeda. It will be a larger, more elliptical galaxy, different from either of its parents. The neat spiral arms that characterize both current galaxies will be disrupted, arms eventually fade, replaced by the more random stellar distribution typical of elliptical galaxies. What's particularly beautiful about this cosmic collision is how it represents both an ending and a beginning. The Milky Way and Andromeda as we know them will cease to exist, but their merger will create something new, a galaxy enriched by the combined stellar populations, gas reserves, and evolutionary history of both parents. It's like a cosmic marriage that creates something greater than the sum of its parts. The collision also reminds us of our place in cosmic time. Humans have existed for only a tiny fraction of the time that will pass before this galactic merger occurs. We're witnessing the universe during a particular era when galaxies are still distinct and separate, when the night sky shows us the orderly spiral structure of our home galaxy. Future beings will inhabit a universe that looks very different from ours. As you drift towards sleep tonight, look up toward the constellation Andromeda if you can see it, or simply imagine it hanging in the northern sky. That faint patch of light contains 1 trillion stars, all racing toward us in the universe's most patient, once inevitable cosmic event. In the vast scale of cosmic time, Andromeda is practically next door, and our galactic collision is practically tomorrow. It's oddly comforting to know that even galaxies have appointments to keep, cosmic dates that were set in motion billions of years ago, and will be kept billions of years in the future, when the universe will witness the beautiful merger of our island home with its nearest neighbor. In all the vastness of space, there exists a silence so complete, so profound, that it challenges our very understanding of what silence means. It's not the quiet of a library or the hush of a snowy night. It's the absolute absence of sound itself. A silence so perfect that no human has ever truly experienced it, except for the few astronauts who have ventured beyond Earth's protective atmospheric embrace. This cosmic silence exists because sound as we understand it simply cannot exist in the vacuum of space. Sound waves are vibrations that travel through matter, through air molecules, bouncing against each other, carrying energy from one place to another, like a cosmic game of telephone. But space is almost entirely empty, with so few particles that there's nothing for sound waves to travel through. It's like trying to make ripples in a pond that has no water. The silence of space means that all the dramatic cosmic events we imagine as thunderously loud actually happen in perfect quiet. When stars explode in supernovas, releasing more energy in seconds than our sun will produce in its entire lifetime. They do so in complete silence. The explosion creates light, radiation, and shockwaves that ripple through any nearby gas and dust, but no sound. It's like watching the universe's most spectacular fireworks display with the volume permanently turned off. This silence extends to everything in space. Planets don't make noise as they orbit their stars. Moons don't whisper as they circle their planets. The solar wind, a stream of charged particles flowing from the sun at over 1,000,000 miles per hour, rushes past in complete silence. Even when asteroids collide at tremendous speeds, creating impacts that would be deafeningly loud if they happened in Earth's atmosphere, they occur in the muffled silence of vacuum. The International Space Station orbits Earth at over 17,000 miles per hour, but it makes no sound as it races through space. Astronauts inside the station can hear each other talk, footsteps on the metal floors, the hum of life support systems, but these sounds travel through the air inside the station. Outside, the station's hull moves through the vacuum in perfect silence, like a ghost ship sailing through an ocean that has no waves. This cosmic silence has practical implications for space exploration. Spacecraft can't use sound-based navigation or communication systems in the vacuum of space. There's no way to hear approaching debris, no acoustic warning of nearby objects. Everything must be detected through electromagnetic signals, visual observation, or other means that don't rely on sound waves. It's like navigating a world where one of your primary senses simply doesn't work. The silence of space also means that all the sounds we associate with space in movies, the roar of spaceships, the whoosh of passing asteroids, the rumble of explosions, are products of artistic imagination rather than physics. Real space travel would be eerily quiet from the outside perspective, with spacecraft moving like silent bullets through the vacuum, their engines creating thrust through the ejection of hot gases, but producing no sound that could travel through space itself. But space isn't entirely devoid of ways to transmit information. While sound waves can't travel through vacuum, electromagnetic waves, radio signals, light, X-rays, and gamma rays all propagate perfectly through empty space, carrying information across vast distances. It's as if the universe replaced sound with light as its primary means of long-distance communication. Some of the most violent events in the universe occur in this perfect silence. Black holes tear apart stars, galaxies collide over millions of years, and cosmic rays accelerate to near-light speeds, all without making a sound. The only way we know about these events is through the electromagnetic radiation they produce, the light, radio waves, and other forms of energy that travel across billions of light-years to reach our telescopes. Near planets with atmospheres, the situation changes dramatically. On Mars, with its thin atmosphere, sounds would be audible but muffled and distorted. A conversation on Mars would sound strange to Earth-trained ears, with higher-pitched sounds fading faster than lower ones due to the different atmospheric composition. On Venus, with its thick atmosphere, sounds might carry further and differently than on Earth, though the crushing pressure and sulfuric acid clouds would make conversation an academic point. The silence of space also gives us a new appreciation for Earth's noisy atmosphere. Every sound you hear, every voice, every musical note, every rustle of wind through leaves, exists because our planet is wrapped in a thin layer of air that can carry vibrations from their source to your ears. The sounds of Earth are made possible by the same atmospheric blanket that protects us from space radiation and maintains the pressure that keeps our bodies from boiling. For astronauts, the silence of space creates a unique form of isolation. In their spacesuits during spacewalks, they can hear their own breathing, their heartbeat, the hum of life support systems, but the universe around them is utterly quiet. Earth hangs below them in complete silence, its storms and oceans and forests, making no sound that can reach through the vacuum. As you settle into the comfortable sounds of Earth tonight, perhaps the distant hum of traffic, the whisper of wind, the settling of your house, remember that these sounds exist only because you're surrounded by an atmosphere that can carry them. Beyond that thin shell of air, the universe continues its grand performance in perfect eternal silence. Stars being born and dying, planets spinning, and galaxies dancing through space without making a sound. In space, no one can hear anything at all, and perhaps that makes the sounds of our small blue world all the more precious. Take a moment to imagine every beach you've ever seen. Picture the endless stretches of sand on tropical shores, the countless grains beneath your feet during summer vacations, the dunes that stretch to the horizon in coastal deserts. Now imagine every beach on Earth, every grain of sand on every shore, in every desert, in every sand box and hourglass. The number is staggering, almost incomprehensible. Scientists estimate there are roughly 7.5 quintillion grains of sand on all of Earth's beaches and deserts combined. That's a 7, followed by 18 zeros, a number so large that if you tried to count to it at one number per second, it would take you longer than the universe has existed. It seems like the ultimate example of countless, until you look up at the night sky and realize that the universe has casually exceeded even this mind-bending quantity. There are more stars in the observable universe than there are grains of sand on Earth. Not just more, but vastly more, perhaps 1,000 times more, maybe 10,000 times more. When astronomers estimate the total number of stars, they arrive at figures around 10 sextillion, a number so large that it makes our beach sand count look modest by comparison. This cosmic abundance becomes even more amazing when you consider what we're actually seeing when we look up at night. On a perfectly clear, dark night, far from city lights, the human eye can see only about 2,000 to 3,000 individual stars. That's roughly the number of grains of sand you might hold in your cupped hand. Yet this handful represents only the tiniest fraction of the stars in our own galaxy, and our galaxy is just one of hundreds of billions of other galaxies, each containing hundreds of billions of stars. The Milky Way alone contains an estimated 200 to 400 billion stars. If you could count one star per second, it would take you over 6,000 years just to count the stars in our home galaxy. And our galaxy is considered fairly typical, not particularly large or small, not unusually dense or sparse. It's a standard-issue spiral galaxy among the cosmic multitudes. But the observable universe contains at least 100 billion galaxies, possibly as many as 2 trillion. Each galaxy represents another vast collection of stars, another island universe with its own stellar population. Some galaxies are much larger than ours, containing trillions of stars. Others are smaller, dwarf galaxies with only billions of stars. When you multiply these galactic populations together, you arrive at numbers that challenge human comprehension. What makes this stellar abundance even more remarkable is that we're only counting the stars we can theoretically observe. The observable universe is limited by the speed of light and the age of the universe. We can only see stars whose light has had time to reach us since the Big Bang. Beyond the observable universe, there's likely much more cosmos containing vastly more stars, but their light simply hasn't had time to travel to us yet. Each of those countless stars represents a massive nuclear furnace, converting hydrogen into helium and releasing tremendous amounts of energy in the process. Every star is a sun, many of them larger and brighter than our own sun. Some stars are so massive they could contain our entire solar system within their circumference. Others are so dense that a teaspoon of their material would weigh as much as a mountain. The variety among these stars is as staggering as their number. There are red giants so large that if one replaced our sun, its surface would extend beyond the orbit of Mars. There are white dwarfs so dense that their gravity would instantly crush anything on their surface. There are neutron stars that spin hundreds of times per second, and stellar remnants so massive they collapse into black holes where even light cannot escape. Many of these stars likely have planets orbiting them, just as planets orbit our sun. If even a small fraction of stars have planetary systems, then the number of planets in the universe dwarfs even the stellar count. And if even a tiny fraction of those planets can support life, then the universe might be teeming with living worlds, each with its own unique story of biological evolution. The abundance of stars also means that the universe is constantly creating new heavy elements through stellar nucleosynthesis. Every star is a cosmic factory, forging carbon, oxygen, iron, and other elements essential for planets and life. When massive stars die in supernova explosions, they scatter these elements through space, enriching the gas clouds that will eventually form new stars and planets. The iron in your blood, the calcium in your bones, and the carbon in your DNA were all forged in the cores of ancient stars. This stellar abundance also provides a humbling perspective on our place in the cosmos. Our Sun is just one ordinary star among the vast multitudes, orbiting in the suburbs of a typical galaxy among billions of other galaxies. Yet somehow, around this unremarkable star, on the third planet out, complexity has emerged that can contemplate the very immensity that contains it. As you prepare for sleep tonight, consider that every grain of sand on every beach on Earth could represent a star, and there would still be thousands of times more stars remaining uncounted in the cosmic inventory. Somewhere among those countless stellar furnaces, other worlds might be spinning through space, possibly harboring other forms of life that are also looking up at their night skies and marveling at the abundance of stars. In a universe so rich with stars, we are all made of ancient stardust, temporary arrangements of cosmic material that briefly awakens to consciousness and wonders at the stellar multitudes that gave us birth. Every 90 minutes, the International Space Station completes a full orbit around Earth, traveling at the staggering speed of 17,500 miles per hour. To put that in perspective, the ISS moves so fast that it could fly from New York to Los Angeles in about 10 minutes, or circle the equator in the time it takes you to eat lunch. This incredible velocity means that astronauts aboard the station experience something no human in history has ever experienced on a regular basis: 16 sunrises and 16 sunsets every single day. Imagine trying to adjust your sleep schedule to that rhythm, just as you're settling in to watch a beautiful sunset with Earth's Terminator line, the boundary between day and night, sliding across continents and oceans below. You know that in just 45 minutes, you'll be watching the sun rise again on the opposite side of the planet. The station's orbital speed means that the traditional 24-hour day becomes a meaningless concept, replaced by a dizzying cycle of light and darkness that cycles through every hour and a half. This high-speed orbital dance isn't arbitrary. It's precisely calculated to maintain the ISS's altitude of roughly 250 to 260 miles above Earth. At this height, the station experiences just enough atmospheric drag to gradually slow it down and lower its orbit over time. To counteract this, the ISS must periodically boost its altitude using thruster burns, essentially speeding up to stay in the same place. It's like riding a bicycle that's constantly slowing down due to friction, requiring periodic pedaling to maintain speed. The station's path around Earth follows what's called a ground track, and this track shifts westward with each orbit due to Earth's rotation. While the ISS completes one orbit in 90 minutes, Earth rotates about 22.5 degrees during that same period. This means that if the station passes over New York on one orbit, it will pass over the Atlantic Ocean on the next orbit, gradually working its way around the globe. Over the course of a day, the ISS traces a complex pattern that eventually covers most of Earth's surface between 51.6 degrees north and south latitude. For the astronauts aboard, this rapid orbital motion creates a unique perspective on Earth's geography and weather systems. They can watch hurricanes swirl across entire ocean basins, observe the aurora dancing at the poles, see city lights twinkling like scattered jewels as they pass over the night side of the planet. Lightning storms appear as brief flashes beneath clouds, and the thin blue line of Earth's atmosphere, the only thing protecting all life on our planet, becomes viscerally apparent when viewed edge-on from space. The speed of the ISS also means that astronauts experience time dilation effects predicted by Einstein's theory of relativity, though these effects are incredibly small. Due to their high velocity and slightly reduced gravitational field at orbital altitude, time aboard the ISS passes very slightly faster than time on Earth's surface, about 0.01 seconds per year. It's not enough to notice without atomic clocks, but it's a real demonstration of relativistic physics in action. Living at this orbital velocity requires careful planning for even simple activities. When astronauts conduct spacewalks, they're also traveling at 17,500 miles per hour, orbiting Earth in their spacesuits. If an astronaut accidentally let go of a tool during a spacewalk, that tool would continue orbiting Earth at the same speed, potentially becoming a piece of dangerous space debris. Every action in space must account for this constant, high-speed motion. The station's rapid orbit also affects communication with Earth. Ground stations can only maintain contact with the ISS when the station is above their horizon, which typically lasts only 10 to 15 minutes per pass. This creates a complex communication schedule involving multiple ground stations around the world and relay satellites to maintain consistent contact with the crew. Photography from the ISS presents unique challenges due to the orbital speed. Astronauts must use fast shutter speeds to avoid motion blur when photographing Earth's surface. Despite this challenge, they've captured some of the most stunning images of our planet ever taken, showing Earth from a perspective that reveals both its beauty and its fragility. The constant motion also means that the ISS experiences rapid temperature changes as it moves in and out of Earth's shadow. In sunlight, the station's surfaces can reach 250 degrees Fahrenheit, while in Earth's shadow, temperatures can drop to -250 degrees. The station's thermal control systems must constantly adjust to these extreme temperature swings that occur every 45 minutes. For the astronauts, the sensation of moving at 17,500 miles per hour is strangely absent. There's no wind resistance in the vacuum of space, no sound of rushing air, no feeling of movement. The station and everything in it are in free fall together, creating the weightless environment that allows astronauts to float effortlessly through the modules. It's only when looking out the windows at Earth, passing by below, that the incredible speed becomes apparent. The ISS's high-speed orbit also serves as a reminder of the precise balance required for spaceflight. The station must travel at exactly the right speed to maintain its orbit. Too slow, and it would fall toward Earth. Too fast, and it would escape into higher orbit, or even leave Earth's gravitational influence entirely. This delicate balance has been maintained for over 2 decades, with the ISS serving as humanity's constant presence in space. As you drift towards sleep tonight, consider that while you're lying still in your bed, there are people 250 miles above you racing around the planet at 5 miles per second, watching the Earth turn beneath them and experiencing a sunrise every 90 minutes in humanity's most remarkable high-speed home among the stars. At the center of every galaxy, including our own Milky Way, lurks something that seems almost too strange to be real: a supermassive black hole, an object so massive and dense that it warps space and time around itself like a cosmic whirlpool. These aren't the garden-variety black holes formed when massive stars collapse. These are monsters containing millions or billions of times the mass of our Sun, sitting at the gravitational heart of every major galaxy in the universe. Our own galaxy's central black hole, known as Sagittarius A*, pronounced Sagittarius A star, contains about 4 million solar masses compressed into a region smaller than our solar system. To put this in perspective, if you could somehow stand at the edge of this black hole's event horizon, the point of no return, where not even light can escape, you would be looking at an object that could contain 4 million stars like our Sun, all collapsed into a space so small that light takes only about 13 minutes to travel across it. These supermassive black holes aren't just passengers riding along in their galaxies. They're the conductors of a cosmic orchestra, influencing star formation, gas flows, and the overall structure of their host galaxies through their immense gravitational pull. The relationship between a galaxy and its central black hole is so intimate that astronomers have discovered a direct correlation between the mass of the black hole and the mass of the galaxy's central bulge. It's as if galaxies and their black holes grow up together, each influencing the other's development over cosmic time. The formation of supermassive black holes remains one of astronomy's most intriguing mysteries. How do you create something with millions of times the mass of the Sun in the early universe, when everything was supposedly smaller and less organized? Some theories suggest they formed from the direct collapse of massive gas clouds in the early universe. Others propose they grew from smaller seed black holes that formed from the first generation of stars, then gradually accumulated mass by consuming surrounding matter over billions of years. What's particularly fascinating is that these black holes can regulate their own food supply. When matter falls toward a supermassive black hole, it forms an accretion disk, a swirling whirlpool of superheated gas and dust that can outshine all the stars in the galaxy combined. The energy released by this falling matter can blow powerful winds of gas away from the galaxy's center, temporarily shutting off star formation and starving the black hole of new material. It's a cosmic feedback loop that helps explain why galaxies don't just collapse into their central black holes and disappear. The supermassive black hole at the center of our Milky Way is relatively quiet right now, occasionally snacking on small amounts of gas and dust, but not actively feeding in any dramatic way. However, radio and X-ray observations reveal that it was much more active in the past, and it could wake up again if significant amounts of material fall toward it. Some astronomers predict that when the Milky Way eventually collides with the Andromeda Galaxy in about 4.5 billion years, the merger could funnel gas toward both galaxies' central black holes, causing them to flare to life as brilliant quasars. The event horizon of a supermassive black hole creates one of the most extreme environments imaginable. At this boundary, the gravitational pull becomes so strong that space and time themselves become distorted. If you could somehow survive the journey to the event horizon, which you couldn't, due to the intense gravitational forces that would stretch you into a long, thin shape, time would appear to slow down dramatically relative to observers far away from the black hole. From your perspective, the rest of the universe would appear to speed up, with billions of years of cosmic history potentially unfolding before your eyes in moments. Recent technological advances have allowed astronomers to actually image the supermassive black holes at the centers of galaxies for the first time. The Event Horizon Telescope, a network of radio telescopes around the world working together, has captured images of the black holes in the center of our galaxy and in the galaxy M87. These images show the characteristic shadow of the black hole surrounded by the glowing accretion disk, providing direct visual evidence of these cosmic monsters. The discovery that supermassive black holes exist at the center of every major galaxy has fundamentally changed our understanding of galactic evolution. Rather than being destructive forces that simply consume everything around them, these black holes appear to play a crucial role in shaping their host galaxies. They influence where and when stars form, how gas moves through the galaxy, and even the overall structure of the spiral arms or elliptical shape. Some supermassive black holes are surrounded by jets of material moving at nearly the speed of light, creating cosmic searchlights that can extend for millions of light years beyond their host galaxies. These jets are among the most energetic phenomena in the universe, powered by the rotational energy of the black hole itself as matter spirals inward past the point of no return. As you settle into sleep tonight, consider that our entire galaxy, every star, planet, and particle of cosmic dust is held in a gravitational dance around an object so massive and strange that it challenges our understanding of reality itself. The supermassive black hole at our galaxy's center sits there patiently, invisible to our eyes, but governing the motions of hundreds of billions of stars through the sheer force of its gravitational presence. In the cosmic hierarchy, we orbit the Sun. The Sun orbits the galactic center, and at that center waits something so massive that it bends space and time around itself. A dark heart that somehow gives structure and stability to our entire cosmic neighborhood. When you look up at the night sky, you're not just seeing space, you're looking back through time itself. Every photon of starlight that reaches your eyes began its journey years, decades, centuries, or even billions of years ago, carrying information about the universe as it existed in the distant past. In a very real sense, the night sky is a cosmic time machine, allowing us to witness the history of the universe simply by looking up. The nearest star to our Sun, Proxima Centauri, appears to us as it was 4.2 years ago. When you see its faint red light, you're witnessing photons that left that star's surface when you were 4.2 years younger. If Proxima Centauri suddenly exploded today, we wouldn't know about it until 4.2 years from now. From our perspective, the star would continue to shine normally until its final light finally reached us, carrying the news of its demise across the interstellar void. This time, delay becomes even more dramatic when we look at more distant objects. The Andromeda Galaxy, visible as a faint smudge in autumn skies, appears to us as it was 2.5 million years ago. The light you see from Andromeda began its journey toward Earth, when early human ancestors were first learning to use stone tools. Entire species have evolved and gone extinct on Earth, while that light traveled through space to reach your eyes. But astronomers have pushed this cosmic time travel much further. Using powerful telescopes, they can observe galaxies whose light has been traveling toward us for over 13 billion years, from when the universe was only 400 to 800 million years old. These ancient galaxies appear as they were during the universe's cosmic dawn, when the first stars were forming and the first galaxies were taking shape. We're literally seeing baby photos of the universe's earliest structures. The Hubble Space Telescope's deep field images reveal thousands of galaxies in patches of sky that appear empty to the naked eye. Many of these galaxies appear as they were over 10 billion years ago, when the universe was fundamentally different from today. These ancient galaxies were often smaller, more irregular, and undergoing rapid star formation as they built up their stellar populations for the first time. What makes this cosmic archaeology even more remarkable is that we can watch the universe evolve by comparing galaxies at different distances, and therefore different ages. Nearby galaxies show us what mature galactic systems look like after billions of years of evolution. Intermediate distance galaxies reveal the universe during its middle age. The most distant galaxies show us cosmic adolescence, when everything was more chaotic and star formation rates were much higher. The James Webb Space Telescope has pushed this time travel even further back, capturing light from galaxies that formed when the universe was only 300 to 400 million years old. These observations are rewriting our understanding of how quickly galaxies could form and grow in the early universe. Some of these ancient galaxies appear surprisingly large and well-organized for their young age, challenging theories about how structure developed in the early cosmos. This backwards time travel through light also reveals the universe's expansion history. Light from distant galaxies is stretched to longer, redder wavelengths due to the expansion of space itself during the billions of years it took to reach us. By measuring this redshift, astronomers can determine not only how far away these galaxies are, but also how fast the universe was expanding at different periods in its history. The cosmic microwave background radiation takes this time travel to its ultimate extreme. This faint glow, detectable by sensitive radio telescopes, comes from the moment when the universe first became transparent to light, about 380,000 years after the Big Bang. When we observe this radiation, we're seeing the universe as it was during its cosmic infancy, long before any stars or galaxies existed. What's particularly beautiful about this cosmic time travel is that it's happening constantly, all around us. The sunlight warming your face left the sun's surface about 8 minutes and 20 seconds ago. The light from Jupiter takes between 33 to 52 minutes to reach Earth, depending on where the planet is in its orbit. Even the light from your reading lamp took a tiny fraction of a second to travel from the bulb to your eyes, though this delay is so brief that it's imperceptible. This time, delay also means that in a very real sense, simultaneity doesn't exist in the universe. There's no universal now that applies everywhere at once. When we say something is happening right now on a distant star, we can only know about it when the light carrying that information finally reaches us. The universe is filled with events that have already happened but haven't been revealed to us yet, and other events that we're witnessing now but that actually occurred in the distant past. For astronomers, this cosmic time travel provides a unique research opportunity. Unlike historians who must piece together the past from incomplete records, Astronomers can directly observe the ancient universe by looking farther into space. The deeper they look, the further back in time they can see, watching the universe's story unfold from cosmic dawn to the present day. As you prepare for sleep tonight, consider that the light reaching your eyes from the stars overhead carries messages from the past, some from the recent past, others from the distant epochs when the universe was young and strange. Every time you look up at the night sky, you're participating in humanity's greatest time travel experiment, witnessing directly the history of the cosmos written in the language of light itself. In a universe where light takes time to travel, we are all cosmic archaeologists, studying the past through the patient journey of photons across the vast expanses of space and time. In the cold, distant reaches of our solar system, where sunlight arrives 900 times dimmer than it does on Earth, Neptune pursues the most leisurely orbit of all the planets. A single year on Neptune lasts 165 Earth years, which means that since its discovery in 1846, this ice giant has completed only one full orbit around the Sun. In fact, Neptune didn't complete its first observed orbit until 2011, an event that went largely uncelebrated on Earth, but marked a significant milestone in our understanding of the outer solar system. To put Neptune's glacial orbital pace in perspective, consider that, when Neptune was at the same position in its orbit as it is today, the American Civil War hadn't yet begun. Charles Darwin had recently published On the Origin of Species, and the first transatlantic telegraph cable was still being laid. Photography was in its infancy, and humans wouldn't achieve powered flight for another half-century. Entire civilizations have risen and fallen during what is, for Neptune, just one trip around the Sun. Neptune's distant orbit places it an average of 2.8 billion miles from the Sun, so far away that it receives less than 1% of the sunlight that Earth enjoys. From Neptune's perspective, the Sun would appear as just a very bright star, roughly the same size that Venus appears from Earth. Despite this cosmic distance, the Sun's gravitational influence is still strong enough to keep Neptune locked in its orbital dance, a testament to the incredible reach of gravitational forces across the solar system. The length of Neptune's year has profound implications for the concept of seasons on this distant world. Neptune's axial tilt is similar to Earth's, which means it experiences seasons as different hemispheres receive varying amounts of sunlight during its long orbit. But a Neptunian season lasts about 40 Earth years. If you were born during Neptune's spring, you could live an entire human lifetime and die of old age before summer arrived. Entire generations of humans pass away during what is, for Neptune, just a change from spring to summer. These extraordinarily long seasons create weather patterns unlike anything we experience on Earth. Neptune's atmosphere, composed primarily of hydrogen, helium, and methane, maintains some of the most dynamic and violent weather in the solar system. Despite receiving so little solar energy, wind speeds on Neptune can reach up to 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic winds race around the planet in bands driven by internal heat sources that we're still working to understand. The methane in Neptune's atmosphere gives the planet its distinctive blue color, but it also creates seasonal changes that unfold over decades. As different hemispheres of the planet tilt toward the distant Sun during Neptune's long year, subtle changes in atmospheric chemistry and circulation patterns develop slowly, like a planet-wide mood change that takes human generations to complete. Neptune's discovery itself is a testament to the precision of orbital mechanics and gravitational theory. The planet was found not through direct observation, but through mathematical prediction. Astronomers noticed that Uranus wasn't following its predicted orbit exactly, and they hypothesized that another planet's gravitational influence was causing these orbital perturbations. Using nothing but mathematics and Newton's laws of gravitation, they calculated where this unknown planet should be, and when they pointed their telescopes to that spot in the sky, there was Neptune, right where the math said it should be. The planet's slow orbital motion means that Neptune's position against the background stars changes very gradually. Ancient astronomers wouldn't have recognized Neptune as a planet because its motion is so slow that it would appear as a fixed star over the course of human observation periods. Even today, Neptune moves less than 2 degrees per year against the stellar background, slower than the hour hand on a clock appears to move. This leisurely orbital pace also affects our exploration of Neptune. Spacecraft missions to the outer planets must be planned with extraordinary precision because launch windows occur infrequently and the journey takes many years. Voyager 2, launched in 1977, didn't reach Neptune until 1989, a 12-year journey to visit a world where a year lasts 165 Earth years. Currently, no future missions to Neptune are planned, partly because of the enormous timescales involved in reaching and studying this distant world. Neptune's orbital period also influences the dynamics of the entire outer solar system. The gravitational relationship between Neptune and Pluto is particularly interesting. Pluto completes exactly 2 orbits for every 3 Neptune orbits, a relationship called orbital resonance that helps stabilize Pluto's unusual orbit. This cosmic clockwork operates on timescales that span centuries, with the relationship between these distant worlds unfolding slowly over multiple human generations. The long Neptunian year also challenges our Earth-centric concepts of time and change. We're accustomed to thinking of a year as a meaningful unit of time, tied to seasons, birthdays, and the rhythm of life on Earth. But Neptune reminds us that the concept of a year is purely relative to where you happen to live in the solar system. On Neptune, what we consider a normal human lifespan represents less than half a seasonal change. As you settle into sleep tonight, consider that somewhere in the distant darkness beyond all the planets you can see with the naked eye, Neptune continues its patient, 165-year journey around the Sun. Since you were born, this distant world has moved only a tiny fraction of the way through its orbit, like a cosmic minute hand that takes human lifetimes to advance from one hour to the next. In Neptune's leisurely dance around the Sun, we find a reminder that the universe operates on timescales that dwarf human experience, where years stretch across centuries and seasons span the rise and fall of civilizations. On Jupiter, there rages a storm that has been blowing continuously since before Shakespeare wrote Hamlet, before Galileo first turned his telescope toward the heavens, before the Pilgrims landed at Plymouth Rock. The Great Red Spot is a hurricane-like vortex larger than Earth that has been swirling in Jupiter's southern hemisphere for at least 400 years, and possibly much longer. It's a meteorological phenomenon that has outlasted entire civilizations, making it perhaps the most persistent weather system in our solar system. To understand the scale of this storm, imagine a hurricane so large that you could drop Earth into its center and still have room to spare. The Great Red Spot currently measures about 10,000 miles across, roughly the diameter of Earth, though historical observations suggest it was once even larger, perhaps twice Earth's diameter. It's a storm so massive that its winds could engulf entire continents, yet it spins in the thin Jovian atmosphere with a persistence that challenges our understanding of atmospheric dynamics. The storm rotates counterclockwise, completing one full rotation every 6 to 7 Earth days. Wind speeds around its edges reach up to 270 miles per hour, fast enough to turn trees into projectiles and level entire cities. Though of course there are no trees or cities on Jupiter's gaseous surface. These winds have been howling for centuries without any apparent signs of weakening, drawing their energy from Jupiter's internal heat and the complex dynamics of the planet's banded atmosphere. What makes the Great Red Spot's longevity so remarkable is that storms on Earth typically last days or weeks at most. Even the most powerful hurricanes eventually exhaust their energy or encounter conditions that disrupt their structure. But Jupiter's atmosphere operates by different rules. The planet is a gas giant with no solid surface to provide friction that would slow down atmospheric circulation. Instead, the Great Red Spot exists in a relatively stable atmospheric layer where it can persist for centuries, fed by the planet's internal heat source and the energy of surrounding atmospheric flows. The storm's distinctive red coloration has puzzled scientists for decades. The exact chemistry responsible for the color remains uncertain, but it likely involves complex organic compounds created by the interaction of Jupiter's atmospheric gases with sunlight and charged particles from space. These compounds might include sulfur, phosphorus, or hydrocarbons that become concentrated in the storm's high-altitude clouds, giving the Great Red Spot its characteristic brick red hue that distinguishes it from the surrounding cream and brown bands of Jupiter's atmosphere. Recent observations from the Juno spacecraft have revealed that the Great Red Spot extends much deeper into Jupiter's atmosphere than previously thought, possibly reaching depths of 200 miles or more below the visible cloud tops. This makes it not just a surface phenomenon, but a deep atmospheric structure that taps into Jupiter's internal dynamics. The storm appears to be like an enormous atmospheric drill, reaching down into layers of the planet that we're only beginning to understand. Interestingly, the Great Red Spot has been shrinking over the past century and a half. When astronomers first began keeping detailed records in the 1800s, the storm was large enough to fit 3 Earths inside it. Now, it's roughly Earth-sized and appears to be continuing to contract, though very slowly. Some scientists have speculated that the storm might eventually disappear entirely, though others believe it could simply be going through a natural cycle of expansion and contraction that operates on timescales of centuries. Photos. The persistence of the Great Red Spot also provides insights into Jupiter's role as a giant atmospheric laboratory. Unlike Earth's weather, which is driven primarily by solar heating and the planet's rotation, Jupiter's atmospheric dynamics are powered largely by heat flowing from the planet's interior. Jupiter actually radiates more energy into space than it receives from the Sun, making it almost like a failed star that generates its own heat through slow gravitational contraction. This internal heat source helps explain how storms like the Great Red Spot can persist for such extraordinarily long periods. And radiates more energy more. To stored nove, indurita. The storm exists within Jupiter's complex system of atmospheric bands, alternating zones of lighter and darker clouds that circle the planet like enormous conveyor belts moving in opposite directions. The Great Red Spot sits at the boundary between 2 of these bands, where the differential motion creates the shear forces that help maintain the storm's rotation. It's like a massive atmospheric bearing, spinning between 2 rivers of gas flowing in opposite directions. I've univer twinteo, so minsichen, so sti safari safer, so minsichen, if you sachin differe safer. Historical observations of the Great Red Spot provide one of the longest continuous records of any atmospheric phenomenon beyond Earth. Astronomers have been sketching and photographing the storm for over 350 years, creating a unique dataset that shows how the storm has changed over time. These observations reveal that the spot occasionally fades to near invisibility before brightening again, sometimes changes color from deep red to pale orange, and has been slowly drifting westward around the planet throughout recorded history. The longevity of Jupiter's Great Red Spot also reminds us that weather systems in our solar system can operate on timescales that dwarf human experience. While we track hurricanes for days and heat waves for weeks, Jupiter casually maintains a storm that has been raging since before the founding of modern science. It's a meteorological monument to the persistence of atmospheric dynamics on a world where weather patterns can outlast entire species on Earth. As you drift towards sleep tonight, imagine that ancient storm continuing its slow rotation in the darkness of the outer solar system, its winds howling through the Jovian night, just as they have for centuries, marking time on a scale that makes human history seem like a brief moment in the cosmic weather report. One of the most surprising side effects of spaceflight sounds like something from a science fiction story. Astronauts grow taller in space, not just a little bit taller, but measurably, noticeably taller, typically gaining about 2 inches in height during their stay aboard the International Space Station. This isn't some optical illusion or measurement error. It's a real physical change that happens to every human body when it escapes Earth's gravitational embrace. The secret lies in your spine, that remarkable column of vertebrae that keeps you upright and allows you to walk, run, and dance through life on Earth. Between each of your vertebrae are soft, cushiony discs made of cartilage and filled with a gel-like substance. On Earth, these discs are constantly compressed by gravity, not just the weight of your body, but the constant downward pull that affects every cell, every molecule, every atom of your being. Think about how you feel at the end of a long day. You might notice that you're slightly shorter in the evening than you were in the morning. This isn't your imagination. Throughout the day, gravity gradually compresses your spinal discs, causing you to lose about half an inch of height from morning to night. When you sleep, lying horizontal relieves some of this compression, allowing your spine to stretch back to its full length. It's a daily cycle of compression and decompression that most people never notice, but that affects everyone who lives under gravity's influence. In space, this gravitational compression disappears entirely. Without the constant downward force of gravity, the spinal discs begin to expand, like sponges that have been squeezed and are now allowed to return to their natural shape. The cartilage absorbs more fluid, the gel-like center of each disc spreads out, and the natural curves of the spine begin to straighten. Over the course of several days in space, this expansion can add up to 2 inches or more to an astronaut's height. This spinal stretching happens remarkably quickly. Astronauts report feeling the effects within hours of reaching orbit, describing sensations of their backs, stretching and sometimes experiencing back pain as their spines adjust to the weightless environment. It's as if their bodies are literally unfolding after a lifetime of being compressed by Earth's gravity. The height increase isn't the only change that happens to the human body in space. The entire muscular and skeletal system begins to adapt to the weightless environment in ways that reveal just how much our bodies are designed for life under gravity. Without the constant resistance provided by their own weight, astronauts' muscles begin to atrophy and their bones start to lose density. These changes require carefully planned exercise routines using specialized equipment to counteract the effects of weightlessness. The spinal changes also affect how astronauts fit into their equipment. Spacesuits and seats aboard spacecraft must be designed to accommodate these height variations, ensuring that life support systems, helmets, and restraints continue to fit properly, even as crew members' bodies change shape during their missions. It's a unique engineering challenge, designing equipment for humans whose physical dimensions are constantly shifting. What's particularly fascinating is that this spinal expansion reveals something fundamental about how our bodies have evolved to live on Earth. The compression of our spinal discs isn't a design flaw or an unfortunate side effect of gravity. It's an integral part of how our bodies function. The constant downward force helps maintain bone density, muscle strength, and even the proper circulation of fluids throughout our bodies. Remove gravity, and the carefully balanced system that evolution has perfected over millions of years begins to change rapidly. The height increase is temporary. Unfortunately for anyone who might enjoy being taller, when astronauts return to Earth, gravity immediately begins compressing their spines again. Within hours of landing, they start losing the extra height they gained in space, and within days or weeks, they're back to their original stature. The return to normal height can sometimes be accompanied by back pain as the spine readjusts to Earth's gravitational field. This temporary growth also affects astronauts' sense of balance and spatial orientation when they return to Earth. Having spent weeks or months in a body that's literally a different shape, they must readjust to their Earth-bound proportions. Simple actions like reaching for objects or walking through doorways can feel strange until their brains recalibrate to their restored Earth-height bodies. The spinal changes experienced by astronauts also provide valuable insights for medical research on Earth. Understanding how the spine responds to the absence of gravity helps scientists better understand spinal compression, disc degeneration, and back pain, conditions that affect millions of people who never leave Earth's surface. The space program inadvertently became a laboratory for studying human physiology under extreme conditions. Some researchers have even speculated about the long-term implications of these changes for future space colonization. If humans were to live permanently in low-gravity environments like Mars or in space stations, how would our bodies adapt over generations? Would children born and raised in low gravity grow taller than their Earth-bound relatives? These questions remain largely theoretical, but the height changes experienced by current astronauts provide the first clues about how human physiology might adapt to life beyond Earth. As you settle into sleep tonight, feel the weight of your body against your mattress, that familiar sensation of gravity pulling you down into comfort. Your spine is slowly decompressing from the day's activities, your discs expanding slightly as you lie horizontal. In space, astronauts experience this decompression continuously, growing taller as they float weightlessly through their orbital home, their bodies temporarily freed from the gravitational constraints that have shaped human evolution for millions of years. In a surprising cosmic twist, the coldest place in the known universe isn't found in the depths of interstellar space or in the shadow of a distant moon. It's right here on Earth, in carefully controlled laboratory conditions, where scientists have achieved temperatures so cold they make the vacuum of space seem toasty by comparison. These ultra-low temperatures, just billionths of a degree above absolute zero, are colder than anything that occurs naturally anywhere in the cosmos. Absolute zero, the theoretical temperature at which all atomic motion ceases, sits at -459.67 degrees Fahrenheit, or -273.15 degrees Celsius. It's the ultimate cold, a temperature so extreme that atoms would essentially stop vibrating entirely if it could ever be reached. While space itself averages about 2.7 degrees above absolute zero, due to the cosmic microwave background radiation left over from the Big Bang, scientists in Earth laboratories have achieved temperatures as low as 1/1000th of a degree above absolute zero. To put this in perspective, these laboratory temperatures are hundreds of times colder than the coldest natural temperatures found anywhere in space. Holder, the shadowed craters at the moon's poles, some of the coldest places in our solar system, Holdestone, reach temperatures of about -400 degrees Fahrenheit, practically balmy compared to what physicists can achieve in their ultra-cold laboratories. Creating these impossibly cold conditions requires techniques that sound more like magic than science. Scientists use a method called laser cooling, where they trap atoms using carefully tuned laser beams that essentially steal energy from the atom's motion. Imagine trying to slow down a moving car by throwing ping-pong balls at it in just the right way. That's essentially what laser cooling does to atoms, using photons to gradually remove kinetic energy until the atoms slow to a crawl. Another technique, called evaporation cooling, works like a cosmic version of how a hot cup of coffee cools down. The most energetic atoms in a trapped cloud are allowed to escape, leaving behind the slower, colder atoms. By repeating this process many times, scientists can create clouds of atoms so cold that they move at speeds of less than an inch per second, slower than a turtle walks. At these ultra-low temperatures, matter begins to behave in ways that challenge our everyday understanding of physics. Atoms can form a state called a Bose-Einstein condensate, where thousands or millions of individual atoms essentially merge into a single quantum entity. It's as if a crowd of people suddenly began moving in perfect synchronization, acting as one unified being, rather than a collection of individuals. These ultra-cold atomic clouds also exhibit superfluidity, the ability to flow without any friction whatsoever. A superfluid can flow uphill, creep up the sides of containers, and continue flowing in loops forever without losing energy. It's matter behaving more like a quantum wave than a collection of individual particles, revealing the strange quantum nature of reality that's normally hidden at everyday temperatures. The creation of these ultra-cold conditions has opened entirely new fields of physics research. Scientists can use these atomic clouds to simulate the behavior of materials under extreme conditions, test fundamental theories about quantum mechanics, and even create artificial gravity fields using laser beams. It's like having a miniature universe in a laboratory where the normal rules of physics can be bent and tested. One of the most remarkable applications of ultra-cold atoms is in the development of atomic clocks, so precise they could run for billions of years without gaining or losing a second. These clocks work by measuring the vibrations of atoms that have been cooled to near absolute zero, eliminating the thermal motion that would normally introduce errors. Such precision has practical applications in GPS satellites, where even tiny timing errors can lead to significant navigation mistakes. The paradox of achieving the universe's coldest temperatures on one of its warmest planets illustrates the power of human ingenuity and scientific understanding. While space provides a naturally cold environment, it's still too warm and chaotic for the ultra-precise conditions needed for these experiments. Earth's laboratories can provide the isolation, control, and specialized equipment necessary to reach temperatures that the universe itself has never achieved naturally. These ultra-cold experiments also help scientists understand what happened during the earliest moments of the universe, when temperatures were dropping rapidly from the incredible heat of the Big Bang. By studying how matter behaves at ultra-low temperatures, physicists can better understand phase transitions and quantum effects that may have played crucial roles in shaping the cosmos during its first fractions of a second. The technology developed for ultra-cold research has also led to advances in quantum computing, where quantum effects are harnessed to perform calculations that would be impossible with conventional computers. The same techniques used to trap and cool atoms can be used to create and manipulate quantum bits, the building blocks of quantum computers that could revolutionize technology in the coming decades. What's particularly beautiful about this achievement is that it represents the triumph of human curiosity over natural limitations. The universe may not provide conditions cold enough for certain experiments, but human ingenuity has found ways to create those conditions artificially, opening new windows into the fundamental nature of reality. As you drift towards sleep tonight, in the comfortable warmth of your Earth temperature environment, consider that somewhere in a laboratory not far away, scientists are creating conditions colder than the depths of interstellar space, manipulating individual atoms with laser beams and magnetic fields to explore the quantum foundations of existence. In pursuing the ultimate cold, we've discovered new states of matter and new ways of understanding the universe, proving that sometimes the most extreme conditions lead to the most profound discoveries. In one of those delightful moments when science fiction becomes science fact, astronomers have discovered that Luke Skywalker's home planet of Tatooine, with its famous double sunset, isn't just a product of Hollywood imagination. Throughout our galaxy, there exist planets that orbit two stars simultaneously, experiencing the alien beauty of binary sunrises and sunsets as part of their everyday reality. These worlds, called circumbinary planets, challenge our Earth-centric assumptions about planetary systems and reveal that the universe is far more creative with solar system architecture than we ever imagined. The first confirmed circumbinary planet, Kepler-16b, was discovered in 2011 by NASA's Kepler Space Telescope. This Saturn-sized world orbits two stars that are locked in their own cosmic dance, circling each other every 41 days, while the planet completes a much larger orbit around both stars every 627 days. From the surface of Kepler-16b, if you could somehow survive its frigid temperatures and lack of a solid surface, you would witness one of the most spectacular sky shows imaginable. Two suns of different sizes and colors, rising and setting at different times, creating complex patterns of light and shadow that change throughout the planet's long year. Binary star systems are actually quite common in our galaxy. Roughly half of all stars exist in binary pairs, or multiple star systems, gravitationally bound companions that orbit their common center of mass. What's remarkable is that stable planetary orbits can exist in such dynamically complex systems. For a planet to maintain a stable orbit around two stars, it must be far enough away that the gravitational influences of both stars blend together smoothly, rather than creating chaotic perturbations that would eventually fling the planet out of the system. The gravitational dynamics of circumbinary systems create unique orbital characteristics. These planets must orbit at distances where the combined gravitational field of the binary star pair creates a stable environment, typically at least 2 to 3 times the distance between the two stars. This means that circumbinary planets tend to have longer orbital periods than planets in single star systems, experiencing years that can last many Earth years while dealing with the complex interplay of gravitational forces from two stellar companions. The discovery of these Tatooine-like worlds has revolutionized our understanding of planet formation. Initially, Many astronomers believed that the chaotic gravitational environment around binary stars would prevent planets from forming at all. The disk of gas and dust from which planets condense would be too disrupted by the competing gravitational influences to allow the gradual accumulation of material into planetary bodies. Yet nature has found ways to create planets even in these challenging environments, suggesting that planet formation is a more robust and adaptable process than we previously thought. Each circumbinary planet discovered so far has unique characteristics that reflect the diversity of binary star systems. Some orbit stars of similar mass and brightness, while others circle mismatched pairs, where one star is much larger and brighter than its companion. Some binary stars are very close together, completing orbits in days, while others are more widely separated with orbital periods of months or years. These variations create different thermal environments and day-night cycles for any planets in the system. The climate patterns on circumbinary planets would be unlike anything on Earth. Depending on the orbital mechanics, these worlds might experience complex seasonal cycles as they orbit around the binary pair. Sometimes both stars would be visible in the sky simultaneously, providing extra heating. Other times, one star might be blocked by the other, creating partial eclipses and unusual lighting conditions. The interplay between the planet's orbit and the star's orbital dance could create climate variations that operate on multiple timescales. Some of the most intriguing circumbinary planets discovered orbit in the habitable zones of their binary star systems, the region where liquid water could potentially exist on a planet's surface. While none of the currently known circumbinary planets are Earth-like rocky worlds, their existence in habitable zones suggests that somewhere in the galaxy there might be worlds with oceans and possibly life, where alien beings witness double sunsets over alien seas. The habitability of circumbinary planets would depend on complex factors, including the masses and temperatures of both stars, the planet's atmospheric composition, and the stability of its orbit over geological timescales. A world orbiting two sun-like stars might be too hot for life, while a planet circling two smaller, cooler red dwarf stars might be just right. The possibilities for creating Earth-like conditions seem vast when you have two stars to work with instead of just one. The discovery techniques for circumbinary planets showcase the ingenuity of modern astronomy. Many of these worlds are found when they pass in front of both stars as seen from Earth, creating complex transit patterns as the planet alternately blocks light from each star. These transit signatures are distinctive and unmistakable, like cosmic fingerprints that reveal the presence of a world dancing around two suns. The existence of circumbinary planets also raises fascinating questions about the potential for life in such systems. Would life that evolved under two suns develop different circadian rhythms? How would photosynthesis work with two stars of potentially different colors and intensities? Would intelligent life that evolved on such worlds naturally think in terms of binary systems and paired concepts? As you prepare for sleep under Earth's single sun, now set below the horizon, imagine worlds where bedtime might come with two sunsets, where the night sky could be illuminated by the light of a second star, and where the very concept of day and night takes on meanings we can barely imagine. In the vast catalogue of possible worlds, circumbinary planets remind us that the universe delights in creating variations on themes we thought we understood, turning science fiction dreams into astronomical reality among the stars. Every second of every day, our sun performs an act of cosmic alchemy that is both beautiful and slightly alarming. It converts 4 million tons of its own mass into pure energy, sending that energy racing across space at the speed of light. This isn't some distant future scenario or theoretical possibility. It's happening right now, as you read these words, as you breathe, as you blink. The sun is literally consuming itself to provide the energy that powers every sunset, every growing plant, every warm day, and ultimately every form of life on Earth. This massive sacrifice occurs deep in the sun's core, where temperatures reach 27 million degrees Fahrenheit and pressures are 250 billion times greater than Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei, individual protons, are slammed together with such force that they overcome their natural electrical repulsion and fuse together to form helium. This process, called nuclear fusion, is the same reaction that powers hydrogen bombs, but in the sun it's controlled and sustained by the perfect balance between gravitational collapse and radiation pressure. The math behind this cosmic energy production is elegantly described by Einstein's famous equation, E equal mc². When four hydrogen nuclei fuse to create one helium nucleus, the helium weighs slightly less than the original hydrogen, about 0.7% less, to be precise. That tiny bit of missing mass doesn't disappear. It's converted directly into energy according to Einstein's equation, where even a small amount of mass, multiplied by the speed of light squared, produces an enormous amount of energy, EA. 4 million tons might sound like an unimaginable amount of mass for the sun to lose every second, but when you consider the sun's total mass, about 2 billion tons, this daily loss is like a human losing a few skin cells. The sun contains enough hydrogen fuel to continue this process for approximately another 5 billion years before it begins to run low on nuclear fuel and enter the next phase of its stellar evolution. The energy produced by each fusion reaction in the sun's core begins an epic journey that can take anywhere from 10,000 to 170,000 years to reach the sun's surface. The photons created by fusion don't travel in straight lines from core to surface. Instead, they bounce around randomly in the dense solar interior, absorbed and re-emitted countless times by atoms in the solar plasma. It's like a photon trying to escape from the world's most crowded room, bumping into obstacles at every turn. Once these photons finally reach the sun's surface, they make the journey to Earth in just over 8 minutes, traveling the 93 million miles between the sun and Earth at light speed. This means that the sunlight warming your face today actually began as fusion reactions in the sun's core sometime during the late Pleistocene epoch, when early humans were still using stone tools and woolly mammoths roamed the Earth. The sun's energy output is so consistent that astronomers have a special term for it, the solar constant. Despite the violent nuclear reactions occurring in its core and the complex magnetic field dynamics that create sunspots and solar flares, the sun varies its energy output by less than 0.1% over an 11-year solar cycle. This remarkable stability has allowed life on Earth to evolve and flourish over billions of years, providing a steady energy source that powers photosynthesis, weather patterns, and the entire food chain. The 4 million tons of mass that the sun converts to energy every second represents just the fuel consumption needed to maintain its current luminosity. During more active periods of the solar cycle, when the sun produces more solar flares and coronal mass ejections, the mass loss can increase slightly. But even during these energetic events, the additional mass loss is negligible compared to the sun's total mass. Wantrier, we feasible to Myers of Howers Ferrier. This continuous mass loss also has a subtle effect on the solar system's dynamics. As the sun loses mass, its gravitational pull on the planets decreases very slightly, causing all planetary orbits to expand gradually over time. Earth's orbit increases by about 1.5 centimeters per year due to this effect, not enough to notice in human lifetimes, but significant over the billions of years of solar system evolution. The nuclear reactions powering the sun also produce neutrinos, nearly massless particles that barely interact with matter and stream out from the sun's core at nearly the speed of light. Billions of these solar neutrinos pass through every square centimeter of your body every second, having traveled directly from the nuclear furnace at the sun's heart. Unlike photons, neutrinos can escape from the sun's core in just a few seconds, making them messengers that carry real-time information about the nuclear processes occurring in the sun's interior. Understanding the sun's mass-to-energy conversion has also provided insights into stellar evolution throughout the universe. Every star in the night sky is performing the same cosmic alchemy, converting its mass into energy at rates that depend on the star's size, temperature, and composition. Massive stars burn through their nuclear fuel much faster than smaller stars, leading to dramatic explosions when they exhaust their hydrogen supplies. As you settle into sleep tonight, warmed by the residual heat of a day powered by sunlight, consider that every calorie of energy that keeps you alive ultimately traces back to those 4 million tons of solar mass that were converted to energy roughly 50,000 years ago. The sun's generous sacrifice of its own substance makes possible every heartbeat, every thought, every dream, a reminder that we are all sustained by our star's patient consumption of itself, one fusion reaction at a time. In the cold outer reaches of our solar system, orbiting Saturn among dozens of other moons, a small icy world called Enceladus puts on one of the most spectacular displays in the solar system. From cracks near its south pole, this moon shoots towering geysers of water, ice, and vapor nearly 500 miles into space. Fountains so tall they could reach from Earth's surface to the International Space Station and beyond. These aren't gentle steam vents or modest hot springs. They're cosmic geysers that launch material at speeds of over 800 miles per hour, creating a glittering display that makes Enceladus one of the most dynamic and beautiful worlds we've discovered. Enceladus is a small moon, only about 310 miles across, roughly the distance from New York to Detroit. You could drive around its equator in about the same time it takes to drive across a large state. Yet from this modest world, geysers erupt with such force that they feed Saturn's E-ring, a vast, diffuse ring of tiny ice particles that extends far beyond Enceladus's orbit. The moon is essentially decorating Saturn's neighborhood with its own frozen breath, spreading ice crystals across hundreds of thousands of miles of space. The geysers emerge from a region near Enceladus's south pole, nicknamed tiger stripes, 4 parallel cracks in the ice surface that appear dark blue in contrast to the bright white of the surrounding terrain. These fractures, with names like Damascus Sulcus and Baghdad Sulcus, are about 80 miles long and roughly a mile wide. They're kept warm by tidal heating from Saturn's gravity, which kneads and flexes Enceladus like a cosmic stress ball, generating internal heat through friction. The discovery of these geysers transformed our understanding of Enceladus from a quiet, frozen moon into one of the most promising places to search for life in our solar system. The water vapor in the geysers suggests the presence of a subsurface ocean beneath the moon's icy crust, an ocean that may contain more water than some of Earth's largest lakes. This hidden sea, warmed by tidal heating and possibly enriched by chemical interactions with Enceladus's rocky core, could provide the 3 essential ingredients for life as we know it: liquid water, chemical energy, and organic compounds. When NASA's Cassini spacecraft flew through the geyser plumes in 2008, it didn't just observe them from a distance, it actually tasted them. The spacecraft's instruments analyzed the composition of the ejected material and found water vapor, ice crystals, carbon dioxide, carbon monoxide, and simple organic molecules, including methane. It was like taking a direct sample from Enceladus's hidden ocean, allowing scientists to study the chemistry of an alien sea without having to drill through miles of ice. The geysers operate on a fascinating schedule, tied to Enceladus's orbit around Saturn. The eruptions are strongest when the moon is farthest from Saturn in its slightly elliptical orbit and weakest when it's closest. This pattern suggests that the tidal forces from Saturn's gravity directly control the geyser activity, opening and closing the tiger stripe fractures like cosmic valves. As Enceladus moves farther from Saturn, the tidal stresses decrease, allowing the cracks to open wider and permitting more vigorous eruptions. The mechanics of how these geysers achieve such incredible heights involve a complex interplay of pressure, temperature, and vacuum conditions. The subsurface ocean is under pressure from the overlying ice shell, but when water finds its way to the surface cracks, it encounters the vacuum of space and instantly begins to vaporize and expand. This explosive decompression, combined with the low gravity on Enceladus, only about 1% of Earth's gravity, allows the water and ice to reach extraordinary altitudes. Individual particles in the geyser plumes follow ballistic trajectories, with some reaching escape velocity and leaving Enceladus entirely to join Saturn's E-ring. Others fall back to the surface, creating a slow but steady redistribution of ice across the moon. This process has likely been ongoing for millions of years, gradually resurfacing parts of Enceladus and creating some of the youngest terrain in the solar system. Some regions of Enceladus appear to be only a few million years old, practically brand new in geological terms. The geyser plumes also create a tenuous atmosphere around Enceladus, composed primarily of water vapor. This atmosphere is incredibly thin, about 100 billion times thinner than Earth's atmosphere, but it's enough to create a slight haze around the Moon and contribute to the complex interactions between Enceladus and Saturn's magnetic field. The discovery of Enceladus's geysers has made this small moon a high-priority target for future exploration. Scientists have proposed missions that would fly repeatedly through the plumes, analyzing their composition in greater detail and searching for more complex organic molecules that might indicate biological processes. Some proposals even envision landing near the Tiger Stripes to study the geyser activity up close and possibly sample material from the subsurface ocean. The geysers of Enceladus also serve as a reminder that the solar system is full of active, dynamic worlds that challenge our preconceptions about where geological activity can occur. This small, distant moon receives only 1% of the sunlight that Earth receives, yet it maintains liquid water and dramatic geological processes through the tidal energy provided by its giant planet host. As you drift towards sleep tonight, imagine those towering fountains of ice and vapor erupting into the vacuum around Saturn, catching the distant sunlight and creating ephemeral rainbows in the space above an alien ocean. On Enceladus, the cosmos has created its own version of Old Faithful, a geyser that shoots not just hundreds of feet into the air, but hundreds of miles into space, decorating the Saturn system with ice crystals and offering tantalizing hints about the hidden ocean world that may harbor some of the solar system's most exciting secrets. Rising from the rust-colored plains of Mars stands a mountain so enormous that it challenges human comprehension. Olympus Mons, a volcanic giant that soars nearly 16 miles above the surrounding terrain, making it almost 3 times taller than Mount Everest. If you could somehow transport this Martian mountain to Earth, its peak would extend well into the stratosphere, reaching altitudes where the sky turns black and the curvature of the planet becomes visible. It's not just the tallest mountain in our solar system, it's a geological monument to the alien nature of planetary processes on Mars. To truly grasp the scale of Olympus Mons, imagine a mountain so wide at its base that you could fit the entire state of Arizona within its footprint. The volcano covers an area of roughly 120,000 square miles, larger than the entire country of Italy. If you stood at the center of this massive shield volcano, the slopes would extend beyond the horizon in every direction, rising so gradually that you might not even realize you were standing on the flanks of the solar system's greatest mountain. Unlike the steep, dramatic peaks we're familiar with on Earth, Olympus Mons has slopes that rise at an angle of only 2 to 5 degrees, so gentle that climbing it would feel more like walking up an extremely long, mild hill than scaling a mountain. You could drive a car up most of its slopes without difficulty, though the journey to the summit would cover hundreds of miles and take you through an environment where the atmospheric pressure drops to less than 1% of Earth's sea level pressure. The formation of Olympus Mons tells a story about Mars that reveals fundamental differences between our planet and the red planet. On Earth, volcanic activity is largely controlled by plate tectonics, the slow movement of crustal plates that eventually carries volcanic regions away from their underlying hotspots. This is why volcanic island chains like Hawaii show a progression of older extinct volcanoes trailing away from the currently active ones. Mars, however, has no active plate tectonics. When a volcanic hotspot develops in the Martian mantle, it stays in one place for hundreds of millions of years, continuously erupting and building up enormous volcanic structures. Olympus Mons is the result of this geological patience, a volcano that has been growing in the same location for perhaps 300 million years, layer upon layer, eruption upon eruption, until it achieved its current massive scale. The volcano sits in a region of Mars called the Tharsis Bulge, where several massive volcanoes cluster together like a family of geological giants. 3 other large volcanoes, Arsia Mars, Pavonis Mars, and Ascraeus Mars, form a line southwest of Olympus Mons, each one impressive in its own right, but dwarfed by their colossal neighbor. Together, these volcanoes create a highland region that rises several miles above the average elevation of Mars. The summit of Olympus Mons features a complex caldera system, a series of overlapping circular depressions created by the collapse of the ground above emptied magma chambers. The largest of these calderas is about 50 miles across and nearly 2 miles deep, large enough to swallow entire cities. These calderas provide evidence of the volcano's long history of eruptions, each depression marking a period when the volcano's internal plumbing emptied and the surface collapsed into the void below. The age of Olympus Mons remains a subject of scientific debate, but crater counting, a technique that estimates the age of planetary surfaces based on the density of impact craters, suggests that some parts of the volcano may be as young as 2 million years old. In geological terms, this is practically yesterday, raising the tantalizing possibility that Olympus Mons might not be completely extinct. While it's certainly not erupting today, it's possible that this massive volcano could awaken again in the future. The atmospheric effects of Olympus Mons would be dramatic for any hypothetical visitors to Mars. The mountain is so tall that its peak extends well above most of the Martian atmosphere, while the atmospheric pressure at the base of the volcano is already thin by Earth standards. At the summit, it drops to less than 1% of Earth's sea level pressure. The peak of Olympus Mons exists in an environment that's almost like space itself. This extreme altitude also means that the summit of Olympus Mons experiences weather patterns completely different from those at lower elevations on Mars. The peak probably never experiences the dust storms that can engulf the rest of the planet, existing instead in the thin, clear upper atmosphere, where temperatures remain extremely cold and ice clouds occasionally form. The discovery and study of Olympus Mons have revolutionized our understanding of volcanic processes throughout the solar system. Its existence demonstrates that planets can build volcanic structures far larger than anything possible on Earth, given the right geological conditions and enough time. The volcano serves as a natural laboratory for understanding how volcanic systems work when they're not disrupted by plate tectonics. Future missions to Mars will likely include Olympus Mons as a target for detailed exploration. The volcano's diverse geological features, from ancient lava flows to relatively young crater formations, could provide insights into Mars's volcanic history and climate evolution. Some scientists have even proposed that the steep cliffs around the volcano's base, scarps that rise up to 4 miles high, might harbor caves or overhangs that could serve as natural shelters for future human explorers. As you settle into sleep tonight, imagine standing at the base of this geological colossus, looking up at slopes that extend beyond the horizon toward a summit hidden in the thin Martian atmosphere. Olympus Mons stands as a monument to the power of geological processes when given enough time and the right conditions, a reminder that the universe creates wonders on scales that dwarf even our most ambitious human constructions. Every morning when you step outside and feel the warmth of sunlight on your face, you're experiencing the end result of an 8-minute and 20-second journey across 93 million miles of empty space. Keurig. Deux bien, Keurig real second. Keurig. The photons touching your skin began their trip from the sun's surface at the exact moment when you were doing something else, perhaps sleeping, eating breakfast, or sitting in traffic, carrying with them the gift of stellar energy that makes all life on Earth possible. This 8-minute journey represents one of the most fundamental constants in our daily experience, yet it's something most of us never think about. The light from our nearest star travels at the ultimate speed limit of the universe, 186,282 miles per second. Yet even at this cosmic speed limit, the vast distance between Earth and the Sun means that we're always seeing our star as it was over 8 minutes ago, never as it exists in the present moment. The journey of a photon from Sun to Earth is remarkably straightforward once it escapes the Sun's surface, but the story of how it got to the surface in the first place is far more complex and time-consuming. The light warming you today actually began as nuclear fusion reactions deep in the Sun's core, somewhere between 10,000 and 170,000 years ago. Those primordial photons bounced around randomly inside the sun for millennia, absorbed and re-emitted countless times, before finally reaching the surface and beginning their 8-minute sprint to Earth. This means that the sunlight you see today carries information about nuclear processes that occurred in the sun's heart during the late Pleistocene epoch, when early humans were developing agriculture and the last ice age was ending. The photons have been patiently working their way through the dense solar interior all this time, like cosmic time capsules carrying ancient stellar energy into our modern world. The 8-minute light travel time also means that if the sun were to suddenly disappear, vanishing completely from existence in some impossible cosmic magic trick, we wouldn't know about it for 8 minutes and 20 seconds. The Earth would continue receiving sunlight, plants would continue photosynthesizing, and solar panels would continue generating electricity for those crucial 8 minutes before the last photons arrived, and we realized our star was gone. It would be the ultimate delayed reaction on a cosmic scale. This time delay becomes even more significant when we consider solar flares and other energetic events on the sun. When astronomers observe a powerful solar flare erupting from the sun's surface, they know that any charged particles accelerated by that flare will arrive at Earth in about 1 to 3 days, potentially disrupting satellites and power grids. But the light from the flare itself, the visual evidence of the explosion, makes the journey in just 8 minutes, serving as an early warning system for the more dangerous particle radiation that follows. The consistency of this 8-minute journey is remarkable when you consider the dynamic nature of the space between Earth and the sun. This region isn't truly empty. It's filled with the solar wind, a stream of charged particles flowing away from the sun at speeds of 300 to 400 miles per second. This but photons, having no electric charge, pass through this solar wind unaffected, maintaining their steady 186, 282 mile per second pace, regardless of the space weather conditions they encounter. The 8-minute light travel time also varies slightly throughout the year due to Earth's elliptical orbit. When Earth is closest to the sun in early January, sunlight takes about 8 minutes and 11 seconds to reach us. When we're farthest from the sun in early July, the journey extends to about 8 minutes and 27 seconds. These variations are small, but they represent real changes in the distance light must travel as Earth follows its slightly oval-shaped orbital path. Understanding the finite speed of light and its travel time from the sun was crucial to developing our modern understanding of the cosmos. Before astronomers measured the speed of light accurately, many believed that light traveled instantaneously. The realization that light has a finite speed and that we see distant objects as they were in the past revolutionized astronomy and led to our understanding of the universe as a vast space-time continuum where distance and time are intimately connected. The 8-minute delay also affects our ability to communicate with spacecraft near the sun. When space missions like the Parker Solar Probe venture close to our star, ground controllers must account for increasingly longer communication delays. As the spacecraft approaches the sun, commands sent to the spacecraft take longer to arrive, and telemetry data takes longer to return to Earth, creating challenging operational conditions for mission planners. This light travel time serves as a perfect introduction to astronomical distances and the vastness of space. If it takes light over 8 minutes to travel from our nearest star, consider that it takes light 4.2 years to reach us from the next nearest star, Proxima Centauri. The light from distant galaxies has been traveling for billions of years, carrying information about the universe as it existed when it was young and very different from today. As you settle into sleep tonight, perhaps after watching the last light of sunset fade from the sky, remember that those final rays of sunlight completed their 8-minute journey from a solar surface that existed briefly in the past, carrying the warmth and energy that powered the day's photosynthesis, weather patterns, and all the countless processes that make Earth a living world. Tomorrow morning's sunrise will bring new photons that are starting their 8-minute journey right now, racing across the vacuum to arrive precisely when you need them to begin a new day. Deep within the turbulent atmospheres of Neptune and Uranus, something extraordinary may be happening that sounds more like a fairy tale than science. Diamonds could be falling like rain. Not tiny specks of diamond dust, but actual diamond crystals, possibly as large as hailstones, formed under conditions of immense pressure and temperature that exist nowhere else in our solar system. These ice giant planets may host the universe's most spectacular and valuable precipitation, where gemstones that would be priceless on Earth cascade through alien skies in an ongoing cosmic storm of crystallized carbon. The diamond rain theory emerged from our understanding of the extreme conditions deep within Neptune and Uranus. These planets aren't gas giants like Jupiter and Saturn. They're ice giants with complex internal structures that include layers of superheated water, methane, and ammonia under pressures millions of times greater than Earth's atmospheric pressure. In these deep atmospheric layers, temperatures reach several thousand degrees Fahrenheit, while pressures climb to levels that can fundamentally alter the behavior of matter. The process begins with methane, a simple molecule composed of carbon and hydrogen that's abundant in the atmospheres of both planets. Under the extreme pressure and temperature conditions found about 5,000 miles below the cloud tops, methane molecules begin to break apart. The intense pressure compresses the liberated carbon atoms so forcefully that they crystallize into diamond, the hardest naturally occurring substance in the universe, formed in the crushing depths of alien worlds. Laboratory experiments on Earth have confirmed that this process is physically possible. Scientists have recreated the pressure and temperature conditions found in the deep atmospheres of Neptune and Uranus, using shock waves to compress methane and other hydrocarbon compounds. These experiments have successfully produced tiny diamonds, proving that the carbon chemistry required for diamond formation can indeed occur under the conditions that exist within ice giant planets. The diamonds formed in these planetary depths wouldn't immediately plummet toward the core. Instead, they would begin a slow descent through layers of increasingly dense material, potentially growing larger as they encounter more carbon-rich compounds during their journey. The low gravity in these deep atmospheric regions, much weaker than what we experience on Earth's surface, would allow these diamond particles to fall relatively slowly, possibly taking thousands of years to make their way through the planet's interior. As the diamonds sink deeper into the planet, they encounter even more extreme conditions. Eventually, the pressure and temperature become so intense that the diamonds themselves begin to melt, forming liquid carbon that may eventually solidify into even larger diamond structures or exotic forms of carbon that don't exist naturally on Earth. It's a geological process unlike anything in our terrestrial experience, where the most precious gemstones become just another phase in the complex chemistry of planetary formation. The scale of this potential diamond precipitation is staggering. Scientists estimate that Neptune and Uranus could be producing thousands of tons of diamonds every year through this process. If these calculations are correct, the interiors of these planets may contain diamond reserves that dwarf anything imaginable on Earth. Not just small gemstones, but potentially massive diamond formations, the size of icebergs floating in seas of liquid carbon. This diamond rain hypothesis also helps explain some puzzling observations about Neptune and Uranus. Both planets generate more heat than they receive from the sun, and the diamond formation process could be one source of this internal energy. As carbon crystallizes into diamond and releases latent heat, and as diamonds later melt under extreme pressure, these phase transitions could contribute to the planet's internal heat budgets. The diamonds on Neptune and Uranus would be unlike any found on Earth. Terrestrial diamonds form over billions of years in the relatively stable environment of Earth's mantle, creating clear, well-structured crystals. The diamonds raining through ice giant atmospheres would form rapidly under chaotic conditions, possibly creating unusual crystal structures, impurities, and colors never seen in earthly gems. They might be black, blue, or entirely transparent, with internal structures reflecting the turbulent conditions of their birth. Recent research has suggested that diamond rain might not be limited to Neptune and Uranus. Jupiter and Saturn also contain methane in their atmospheres, and while their internal structures are different from the ice giants, some regions within these gas giants might also experience conditions suitable for diamond formation. The universe's diamond mines might be more common than we initially thought, hidden in the crushing depths of giant planet atmospheres throughout our solar system and beyond. Intuition and the Hisbolghar. The discovery of potential diamond rain on these distant worlds also influences our understanding of planetary formation and evolution. The presence of large quantities of diamonds in planetary interiors could affect heat transport, internal structure, and magnetic field generation. Diamonds are excellent thermal conductors, so vast diamond formations might help distribute heat throughout these planets' interiors in ways we're only beginning to understand. Future missions to Neptune and Uranus, both of which haven't been visited by spacecraft since Voyager 2's brief encounters in the 1980s, could provide more direct evidence for diamond rain. Atmospheric probes designed to survive the crushing pressures of the deep atmosphere might be able to sample the products of this exotic precipitation directly, bringing back definitive proof of one of the solar system's most valuable weather phenomena. As you drift towards sleep tonight, imagine those distant ice giants spinning slowly in the outer darkness of our solar system, their deep atmospheres alive with the gentle fall of diamond rain. In the alien depths of Neptune and Uranus, Homongous Theoriaminus, the universe casually creates treasures that would be beyond price on Earth, letting them fall like snowflakes through atmospheric layers that no human eye will ever see. A reminder that the cosmos reserves its most spectacular displays for its most hidden places. Launched in 1977, when disco was dominating the airwaves and Star Wars was premiering in theaters, Voyager 1 has become humanity's most distant ambassador, now speaking to us from the space between the stars themselves. After 45 years of travel, this remarkable spacecraft continues to send signals back to Earth from over 14 billion miles away. So far that radio messages from Voyager 1 take more than 22 hours to reach us, traveling at the speed of light across a distance that no human-made object has ever traversed before. To put Voyager 1's incredible journey in perspective, imagine that Earth is a marble sitting on your desk. At this scale, Voyager 1 would be roughly 300 miles away, still moving steadily away from you at the speed of a brisk walk. The spacecraft is traveling through space at about 38,000 miles per hour, fast enough to circle Earth in just 2.5 hours. Yet the vastness of interstellar space is so enormous that even at this tremendous speed, Voyager 1 won't come close to another star for tens of thousands of years. Voyager 1 won't come close to another star for tens of thousands of years. The spacecraft crossed into interstellar space in August 2012, becoming the first human-made object to leave the heliosphere, the vast bubble of charged particles and magnetic field that our sun creates around the solar system. This transition wasn't marked by a dramatic boundary or sudden change, but rather by subtle shifts in the density of charged particles and the direction of magnetic fields that Voyager 1's instruments detected. The spacecraft had entered a realm where the solar wind no longer dominates, replaced by the thin gas and cosmic rays that drift between the stars. What makes Voyager 1's continuing communication even more remarkable is the power source keeping it alive. The spacecraft carries no solar panels at its current distance. Sunlight is far too weak to provide useful energy. Instead, Voyager 1 is powered by 3 radioisotope thermoelectric generators, RTGs, that convert heat from the radioactive decay of plutonium-238 into electricity. These nuclear batteries have been steadily declining in power output for decades, producing about 4 watts less power each year, roughly equivalent to a dim Christmas light bulb. Mission engineers have had to make increasingly difficult decisions about which scientific instruments to keep running as power levels continue to drop. They've turned off non-essential systems, adjusted operational procedures, and even shut down some heaters to conserve energy. Yet somehow Voyager 1 keeps talking, its signals growing fainter each year, but still carrying precious scientific data across the cosmic void. The spacecraft's twin, Voyager 2, follows a different trajectory and reached interstellar space in November 2018. Together, these 2 intrepid explorers are providing humanity's first direct measurements of the space between stars. They've discovered that interstellar space isn't empty, but contains a thin soup of gas, dust, and energetic particles, the raw material from which future stars and planets will form. Voyager 1's data has revealed that interstellar space is filled with cosmic rays, high-energy particles accelerated by distant supernova explosions and other violent cosmic events. These cosmic rays are more intense in interstellar space than they are within our solar system, where the sun's magnetic field provides some protection. The spacecraft is essentially traveling through a universe filled with atomic bullets fired by stellar explosions that occurred millions of years ago. Perhaps most poignantly, Voyager 1 carries humanity's most ambitious message to the cosmos: the Golden Record. This gold-plated copper disc contains sounds and images from Earth, including music by Bach and Beethoven, greetings in 55 languages, sounds of wind and rain, and human heartbeats, and photographs showing the diversity of life on our planet. If extraterrestrial intelligence ever finds Voyager 1, they'll discover not just a piece of human technology, but a love letter from Earth to the universe. The longevity of Voyager 1's mission far exceeds anyone's expectations. Originally designed for a 4-year mission to study Jupiter and Saturn, the spacecraft has operated for more than a decade beyond its planned lifetime. It has witnessed the volcanic eruptions of Jupiter's moon Io, discovered new moons around Saturn, and provided our first close-up views of the outer solar system's most mysterious worlds. As Voyager 1 continues its journey into the galaxy, its path will eventually carry it toward the constellation Ophiuchus, though it will take about 40,000 years to reach the vicinity of the next star in that direction. By that time, human civilization as we know it will have changed beyond recognition, yet this small spacecraft will still be carrying its golden message through the cosmic dark. The spacecraft's ability to maintain contact across such vast distances represents a triumph of both engineering and physics. The radio signals from Voyager 1 are now so weak that the total power collected by all of Earth's radio telescopes since the mission began is less than the energy released by a single snowflake hitting the ground. Yet our most sensitive antennas can still detect these whispers from the edge of forever. Mission scientists estimate that Voyager 1 will continue transmitting data until around 2025, when its power supply will finally drop below the threshold needed to operate its scientific instruments. After that, the spacecraft will continue its silent journey through the galaxy, carrying its golden record and its memories of Earth towards stars that won't be born for millions of years. As you settle into sleep tonight, consider that somewhere in the vast darkness between the stars, a small piece of 1970s human technology continues its patient journey through space, farther from home than any human artifact has ever traveled, still faithfully sending back messages from the cosmic wilderness that lies beyond our sun's protective embrace. Surrounding our planet like an invisible force field from science fiction, Earth's magnetosphere stretches tens of thousands of miles into space, creating a protective bubble that deflects most of the deadly charged particles streaming from the sun. This magnetic shield is so vast that it completely engulfs our planet and extends far beyond the orbit of the moon, yet it's completely invisible to our eyes, detectable only by sensitive instruments, and occasionally revealed through the ethereal dance of the aurora at our planet's poles. The magnetosphere is generated by Earth's molten iron core, which acts like an enormous dynamo spinning deep beneath our feet. As our planet rotates, this liquid metal core moves and swirls, creating electric currents that generate powerful magnetic fields. These fields stretch far out into space, creating a teardrop-shaped magnetic bubble around Earth, with the point of the teardrop extending away from the sun like a cosmic windsock. Without this magnetic protection, Earth would be a very different and far more hostile place. The solar wind, a constant stream of charged particles flowing from the sun at speeds of over 1 million miles per hour, would strip away our atmosphere over geological time, leaving us as barren and airless as Mars. The same stellar radiation that gives us warmth and light would also deliver lethal doses of cosmic radiation that would make complex life nearly impossible on our planet's surface. The magnetosphere doesn't just deflect solar particles, it actively captures some of them, trapping charged particles in radiation belts that surround our planet. These Van Allen radiation belts, discovered in 1958 by the first American satellite mission, contain so much energetic radiation that spacecraft passing through them must be specially shielded to protect their electronics. Astronauts traveling to the moon had to pass quickly through these belts to minimize their radiation exposure. The interaction between the solar wind and Earth's magnetic field creates one of nature's most beautiful displays, the aurora borealis and aurora australis, the northern and southern lights. When charged particles from the sun follow Earth's magnetic field lines down toward the polar regions, they collide with atoms in our atmosphere, causing them to glow in curtains of green, red, blue, and purple light that dance across the polar skies like cosmic spotlights. Earth's magnetic field isn't static. It's constantly fluctuating and changing in response to variations in the solar wind and changes in our planet's deep interior. During periods of high solar activity, when the sun releases powerful solar flares and coronal mass ejections, our magnetosphere can be compressed and distorted, sometimes allowing more charged particles to penetrate closer to Earth's surface. These magnetic storms can disrupt satellite communications, interfere with GPS navigation, and even cause power grid failures on Earth. The magnetic field also provides scientists with a window into Earth's deep interior. By studying how the magnetic field changes over time, geophysicists can learn about the motion of liquid iron in our planet's core, thousands of miles beneath the surface, where no direct observation is possible. These magnetic measurements have revealed that Earth's core is a dynamic churning system with complex circulation patterns that affect everything from the length of our days to the intensity of our magnetic protection. One of the most remarkable aspects of Earth's magnetic field is that it occasionally reverses completely, with magnetic north becoming magnetic south, and vice versa. These magnetic reversals happen every few 100,000 years on average, though the timing is highly irregular. During a reversal, which can take several thousand years to complete, the magnetic field weakens significantly, potentially leaving Earth with reduced protection from cosmic radiation. The last magnetic reversal occurred about 780,000 years ago, and some scientists believe we may be overdue for another one. There's evidence that the magnetic field has been weakening over the past few centuries, and the magnetic North Pole is currently moving from northern Canada towards Siberia at an accelerating pace. While a magnetic reversal wouldn't cause immediate catastrophe, it could affect everything from animal migration patterns to technological systems that rely on magnetic navigation. Earth's magnetic field extends far beyond our planet, creating a complex interaction zone with the solar wind called the magnetopause. This boundary shifts constantly as the pressure from the solar wind varies, sometimes compressing Earth's magnetic field to within 6 Earth radii on the day side, while allowing it to stretch into a long magnetic tail that extends beyond the Moon's orbit on the night side. The study of Earth's magnetosphere has also provided insights into magnetic fields around other planets. Mars once had a strong magnetic field, but lost it billions of years ago, which may explain why it lost most of its atmosphere and became the cold, dry world we see today. Jupiter has an enormous magnetosphere that's even more powerful than Earth's, while Venus has almost no magnetic field at all, leaving its thick atmosphere exposed to the solar wind. Modern life depends heavily on Earth's magnetic protection, though we rarely think about it. Our satellites, power grids, and communication systems all exist within the shelter of the magnetosphere. Without this invisible shield, the electronics that power our modern world would be constantly bombarded by radiation that could damage or destroy them. As you settle into sleep tonight, rest assured that Earth's magnetic field continues its ancient duty to deflecting cosmic radiation and solar particles in a protective embrace that has safeguarded our planet for billions of years. This invisible force field, generated by the motion of molten iron thousands of miles beneath your feet, stands guard between Earth and the hostile radiation environment of space, allowing life to flourish in the gentle shelter of its magnetic embrace. Mars appears red in our night sky for the same reason an old bicycle left outside turns reddish-brown. The entire surface of the red planet is covered in iron oxide, the same compound that forms when iron is exposed to oxygen and water over time. It's a planet-wide patina of rust that gives Mars its distinctive color and tells a story about ancient water, oxygen, and chemical processes that transformed an entire world into the solar system's largest rust bucket. The iron that creates Mars's rusty appearance comes from the planet's volcanic rocks, which contain iron-rich minerals like olivine and pyroxene. When these volcanic materials were exposed to the Martian atmosphere billions of years ago, chemical weathering processes began breaking down the iron-bearing minerals and converting them into iron oxide. Unlike the localized rusting we see on Earth, this process happened on a global scale, gradually coating the entire Martian surface in a layer of rust dust that can be several feet thick in some regions. What makes Mars's rust story particularly interesting is that it requires both oxygen and water, two ingredients that Mars has in very limited quantities today. The presence of so much iron oxide on the surface suggests that ancient Mars had a very different atmosphere and climate than it does now. Billions of years ago, Mars likely had a thicker atmosphere, liquid water flowing on its surface, and possibly even oxygen being produced by unknown processes. The planet was essentially rusting itself, while it still had the atmospheric conditions to support the chemical reactions. The rust on Mars isn't uniformly distributed across the planet. Some regions appear more reddish than others, creating a variegated landscape of different hues and textures. The iron oxide particles are incredibly fine, much smaller than the iron oxide flakes that form on rusted metal on Earth. These tiny particles are easily picked up by Martian winds and distributed throughout the atmosphere, creating the dust storms that can engulf the entire planet and give the Martian sky its butterscotch color. During global dust storms, which can last for months, the iron oxide particles suspended in the atmosphere scatter sunlight in ways that create spectacular but alien sunsets. While sunsets on Earth typically appear red and orange due to our atmosphere scattering blue light, sunsets on Mars can appear blue and green as the iron oxide dust scatters light differently. It's a daily reminder that even familiar phenomena like sunsets can take on completely different characteristics on other worlds. The iron oxide on Mars exists in several different forms, each with its own distinct color and properties. The most common form is hematite, which gives Mars its classic red color, but there's also magamite, goethite, and other iron oxide minerals that create variations in color from bright red to dark reddish-brown to almost black. These different forms of iron oxide tell scientists about the specific conditions under which they formed, providing clues about ancient Martian environments. Some of the most intriguing iron oxide formations on Mars are found in specific geological formations that appear to have formed in the presence of liquid water. These deposits, sometimes called blueberries, because of their small spherical shape, are concretions of hematite that likely formed when iron-rich groundwater evaporated, leaving behind concentrated iron oxide nodules. Finding these formations has been crucial evidence for understanding Mars's watery past. The rusting process on Mars also affects modern exploration of the planet. The fine iron oxide dust clings to everything, coating solar panels on rovers and landers, getting into mechanical joints, and creating challenges for maintaining equipment on the Martian surface. The dust is so fine and clingy that it can reduce the efficiency of solar panels over time, limiting the operational lifespan of some Mars missions. Interestingly, not all of Mars is equally rusty. Some regions show evidence of other minerals and compositions that create different colors and textures. The polar ice caps appear white due to frozen carbon dioxide and water ice, while some volcanic regions show darker colors where fresh lava flows haven't had time to develop thick rust coatings. These variations in surface composition create a complex planetary palette that goes far beyond simple red rust. The iron oxide on Mars also has implications for future human exploration. Iron is a valuable resource for manufacturing and construction, and the abundance of iron oxide on Mars means that future colonists would have access to large quantities of iron if they can develop efficient methods for extracting it from the rust. The oxygen in iron oxide could also potentially be extracted for breathing air or rocket fuel, making Mars's rusty surface a potential resource rather than just a colorful curiosity. Recent discoveries have revealed that some iron oxide formations on Mars may have formed through processes involving subsurface water that persisted long after the planet's surface became cold and dry. These findings suggest that the rusting process on Mars may have continued for much longer than previously thought, possibly even into relatively recent geological time, when underground water systems remained active. The story of Mars's rust is ultimately a story about planetary evolution and the power of chemistry to transform entire worlds. What began as volcanic rocks rich in iron became a planet-wide rust deposit through billions of years of chemical weathering, atmospheric interaction, and possibly biological processes that we're still working to understand. As you settle into sleep tonight, consider that ancient chemical process that painted an entire planet rust red, transforming Mars from whatever color it once was into the distinctive red planet that captures our imagination and calls to us from across the cosmic void. As you settle into sleep tonight, consider that ancient chemical process that painted an entire planet rust red. In the rust of Mars, we see evidence of water, oxygen, and chemical processes that remind us how dynamic and changeable planetary environments can be over deep time. In a universe containing roughly 10 circumflex 80 atoms, a number so large it includes every particle in every star, planet, and grain of cosmic dust across all the galaxies we can observe. It seems like we've reached the ultimate measure of vastness, yet a simple board game sitting in countless homes around the world contains something even more infinite. The number of possible chess games exceeds the number of atoms in the observable universe by such a staggering margin that it challenges our understanding of mathematical infinity itself. The standard estimate for possible chess games is approximately 10 circumflex 120, though some calculations suggest numbers even larger. To put this in perspective, if every atom in the observable universe could somehow play through a different chess game simultaneously, there would still be 10 circumflex 40 more possible games remaining unplayed. It's a number so large that it makes the already incomprehensible vastness of the atomic universe seem almost modest by comparison. This extraordinary complexity emerges from the relatively simple rules of chess. Each game begins with the same starting position, but after just 4 moves by each player, there are already over 300 billion possible positions on the board. The complexity grows exponentially with each move, as players choose from dozens of legal options, each choice branching into multiple new possibilities that branch again into even more possibilities. It's a mathematical explosion of possibility that makes chess perhaps the most complex system ever devised by human minds working within a confined 64-square space. The mathematician Claude Shannon first calculated the complexity of chess in 1950, estimating what's now known as the Shannon number at approximately 10 circumflex 120 possible games. Shannon's calculation was based on an average game lasting about 40 moves with an average of 30 legal moves available at each turn. Even this conservative estimate produces a number that dwarfs the atomic content of the universe, revealing that humans had inadvertently created a system of complexity that rivals the cosmos itself. What makes this comparison even more remarkable is the difference in scale between the physical components. The universe contains its atoms across distances of billions of light-years, in structures so vast that light from distant galaxies takes billions of years to reach us. Chess accomplishes its greater complexity using just 32 pieces on a board that could fit on a small table, proving that mathematical complexity doesn't require physical vastness to achieve cosmic significance. The branching nature of chess complexity means that even if every person who ever lived played chess continuously for their entire lives, trying a different game each time, humanity wouldn't even begin to explore the full space of possible games. If all of human history represented just 1 second, you'd need trillions upon trillions of years to explore even a tiny fraction of chess's total possibility space. The game contains more unique experiences than could be exhausted by any conceivable intelligence over any conceivable time span. This infinite complexity, within finite rules, has made chess a powerful metaphor for understanding computational complexity, artificial intelligence, and the emergence of vast possibility spaces from simple rule sets. When computer scientists develop chess-playing programs, they're not trying to solve chess completely. Such a task would require computational resources that exceed what's possible, even in principle. Instead, they're developing heuristics and search strategies that can navigate the impossibly vast space of possibilities to find good moves within reasonable time constraints. The comparison between chess complexity and cosmic atoms also illuminates something profound about the nature of information versus matter. The universe's atoms represent the physical substrate of reality, the actual stuff from which everything is made. Chess games represent pure information, patterns and relationships that exist independently of any particular physical implementation. In some sense, chess demonstrates that the realm of possible information structures is vastly larger than the realm of possible material structures. Even more remarkably, chess isn't unique in this respect. Many other combinatorial systems exhibit similar or even greater complexity. The number of possible games of Go, for instance, is estimated to be around 10 circumflex 171, even more vast than chess. Soei has all poetry, music, and literature also contain possibility spaces that dwarf the physical universe. Every possible poem, symphony, or novel that could ever be written represents a unique point in an abstract space of creativity that exceeds cosmic physical reality. This suggests something wonderfully strange about the relationship between mind and universe. Human consciousness, emerging from arrangements of atoms that represent an infinitesimally small fraction of the universe's matter, has discovered ways to create and explore abstract spaces that are mathematically larger than the physical cosmos that contains them. We are, in effect, cosmic dust that has learned to contemplate infinities larger than the universe itself. The chess versus atoms comparison also provides a humbling perspective on artificial intelligence and computational limits. Even as computers become more powerful and chess programs become nearly unbeatable, they're still exploring only the tiniest fraction of chess's total possibility space. The most advanced chess engines use sophisticated algorithms to search millions of positions per second, but they're still constrained to examining only minute portions of the game's total complexity. As you settle into sleep tonight, consider that sitting somewhere in your home or neighborhood, there's probably a simple chess set that contains more unique possibilities than there are atoms in all the stars, planets, and cosmic dust clouds scattered across the observable universe. In 32 pieces and 64 squares, human ingenuity has captured a mathematical infinity that exceeds the physical cosmos itself, a reminder that the most profound vastness isn't always found in the space between stars, but sometimes in the space between thoughts, where infinite possibilities await exploration in the realm of pure idea. At the very edges of the observable universe, something extraordinary is happening that seems to violate one of physics' most fundamental rules. Space itself is expanding faster than the speed of light. This isn't science fiction or theoretical speculation. It's the reality of cosmic expansion in the far reaches of our universe, where the fabric of space-time stretches so rapidly that distant galaxies are receding from us at velocities that exceed light speed itself. This faster-than-light expansion doesn't violate Einstein's relativity because it's not matter moving through space at superluminal speeds. It's space itself that's expanding. Imagine an infinite balloon being inflated, with galaxies like dots painted on its surface. As the balloon expands, distant dots move away from each other faster than nearby dots, not because they're moving through the balloon's surface, but because the surface itself is stretching. At cosmic scales, this stretching of space can carry distant galaxies away from us faster than light could travel between them. The boundary where this occurs is called the cosmic event horizon, located at a distance of approximately 16 billion light-years from Earth. Beyond this horizon, galaxies are receding from us so rapidly due to cosmic expansion that light leaving them today will never reach us, no matter how long we wait. It's as if there's an invisible sphere surrounding us, beyond which the universe becomes forever inaccessible, sealed off by the expanding cosmos itself. This cosmic expansion was first discovered by Edwin Hubble in the 1920s, when he observed that distant galaxies appeared to be moving away from us, with more distant galaxies receding faster than nearby ones. This relationship, now known as Hubble's law, revealed that the universe itself is expanding uniformly in all directions. But it wasn't until much later that astronomers realized the full implications. At sufficient distances, this expansion exceeds the speed of light. The expansion rate of the universe is described by the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. While this seems modest at first, the effect accumulates with distance. At a distance of about 4,200 megaparsecs, roughly 14 billion light-years, the recession velocity reaches the speed of light, and beyond that distance, galaxies recede faster than light itself. What makes this expansion even more remarkable is that it's accelerating. In 1998, astronomers studying distant supernovae discovered that the expansion of the universe is not slowing down due to gravitational attraction, as most scientists expected, but is actually speeding up. This acceleration is attributed to dark energy, a mysterious force that comprises roughly 68% of the universe's total energy density and appears to be driving space apart at an ever-increasing rate. The faster-than-light expansion has profound implications for our understanding of the observable universe. The galaxies we can see represent only a fraction of the total universe. Beyond our cosmic event horizon lies an infinite expanse of space and matter that will forever remain invisible to us. We exist within what cosmologists call a Hubble bubble, a sphere of observability beyond which the universe races away from us, faster than information can travel. This expansion also affects the light we receive from distant galaxies. Photons from the most distant observable galaxies have been stretched by cosmic expansion during their journey to us, shifting them from ultraviolet and visible wavelengths to infrared and radio wavelengths. This cosmological redshift allows astronomers to measure how much the universe has expanded since the light was emitted, providing a direct measure of cosmic history encoded in the spectrum of distant starlight. The concept of space expanding faster than light also challenges our intuitive understanding of motion and distance. In normal circumstances, we think of objects moving through space, but cosmic expansion involves space itself growing. A galaxy at the edge of the observable universe isn't moving through space at faster than light speed. Instead, the space between us and that galaxy is expanding so rapidly that the cumulative effect exceeds light speed. Future cosmic expansion will gradually isolate our local neighborhood from the rest of the universe. However, when Nivyomafurias, in the far future, as dark energy continues to accelerate cosmic expansion, even nearby galaxy clusters will eventually recede beyond our cosmic event horizon, leaving the Milky Way and its immediate galactic neighbors alone in an expanding sea of darkness. Future astronomers born billions of years from now might see a universe that appears nearly empty, with no evidence of the rich cosmic web of galaxies that we observe today. The faster-than-light expansion also means that there are regions of the universe from which we will never receive any information, no matter how advanced our technology becomes. These regions exist beyond the fundamental limit imposed by the speed of light and the age of the universe, creating an ultimate boundary to human knowledge about the cosmos. Despite this limitation, the observable universe still contains more galaxies, stars, and planets than we can hope to explore or understand in detail. The portion of the universe accessible to our observation includes hundreds of billions of galaxies, each containing hundreds of billions of stars, representing more worlds and possibilities than human civilization could investigate, even with millions of years of technological advancement. As you drift towards sleep tonight, consider that at this very moment, space itself is expanding around you, carrying distant galaxies away from us, faster than light can travel. The universe is writing its own story of expansion and isolation, creating cosmic horizons beyond which even light cannot return to tell us what lies beyond. In the grand symphony of cosmic expansion, we exist within a brief, observable movement of a much larger composition that extends forever beyond the reach of light itself. And so we reach the gentle end of our cosmic wandering, having drifted through diamond planets and ancient storms, past silent voids and singing galaxies. Perhaps these strange space stories have shifted something in how you see the darkness outside your window tonight. The universe, it turns out, is far weirder and more wonderful than we give it credit for. I hope these cosmic tales have left you feeling simultaneously tiny and enormous. Tiny because we're just one small planet, orbiting one ordinary star among countless others. Enormous because we're made of stardust that learned to wonder about itself. Before you fully drift away, I'm curious, are you planning to look up at the stars differently now? Please, if these gentle journeys through space brought you even a moment of wonder, consider subscribing to help me keep exploring the universe's quieter mysteries. Your support lets me continue finding the cosmic stories that transform sleepless nights into peaceful adventures. May your dreams tonight be filled with impossible storms on distant worlds, and may you wake tomorrow carrying just a little more stardust wonder in your everyday world. Sleep well. Fellow traveler of the cosmos,